But we'll get ready for the first talk of today, and that is an invited talk given by Louise Hara, and she will talk about JEDI. So it's the Joint EUV Corona Diagnostic Investigation.
Okay, good morning, everybody. So yes, it's already been mentioned that JEDI is probably the best name for an instrument. So this is the NASA contribution to the ESA FIDGIL mission. And it's an imager, and it's led by Don Hassler from Surrey. He's a PI, and Nikki Fial is a deputy PI and project scientist from Goddard Space Flight Center. And next slide. There we go. Okay, so I know Matt will give the review of FIDGIL later, but just to remind you that the mission will be the first one to be at the L5 point. So these Lagrange points are special points, which is an equilibrium position for small bodies against two larger bodies. So the reason that L5 is so special is that between the Sun and the Earth line, you see the activity before it reaches the Earth, basically. So we know the L1 point very well with our well-loved SOHO mission. That'll be 30 this year. And we'll hear about the Korean L4 mission next. So this is an image from EOI, the EUV imager on solar orbiter, which caught this very large filament eruption, one of many that we've seen. And ESA put together the slide to illustrate the importance of the FIDGIL location relative to solar orbiter, where solar orbiter was at that time. So having this view where you can see things that will be head on towards the Earth is really, really critical. When we're looking straight on towards the Earth, we can't measure the speeds well, we can't see the direction well, and so on. So this is where L5 is super important for space weather. So for the JEDI instruments, it has two parts to it. So it's the space weather operational coronal imager. So this was the aspect which was the #1 criterion for the imager, so SWOC. It has 3 channels. The first one covers helium-2 that we know and love so well, but also is extended so that it covers iron-16. So it's chromospheric with a bit of plasma around 2.5 million degrees as well. And then the second channel is also well known and loved, the 195, the iron-12 and iron-24 channel. And then we have the 133 iron-8, iron-20 channel. So these are the core kind of imaging, the solar disk aspects of it. And then the additional aspect is called the enhanced wide-angle coronal imager. So this is building on work from the EUV imagers and solar orbiter. And this is using an occulter which allows you to see the region where we can't currently see very well. So this is the middle corona that Matt wrote an excellent review on year before last. Time flies. So it's trying to look at this region to connect through to what we will see in the compact coronagraph and so on. So the fields of view, we will be sitting with the SWOC, so the Space Weather Operational Coronal Imager. We'll obviously be sitting with as much field of view this way where we see as much heading towards Earth. So that'll be 3.2 solar radii. And then we've got the EWOC, the enhanced, will be going out to 6 solar radii, and we can observe it with and without the occulter. So JEDI will harness the development of breakthroughs in EUV imaging in middle corona. So there's been a lot of work done. In Proba 2 SWOP has measured out to 2 solar radii. And I've also used off points to allow you to see further out, which has been really nice data sets. GoSUVI as well goes out to 3 solar radii, and they use offset pointing as well to build up these composite images, which have been really amazing. And then Solar Orbiter EUI, the UV imagers, it also uses an occulter. So this is the first time an occulter has been used in extreme ultraviolet. And it's really allowed us, we don't use it a lot, but it has allowed us to test whether you can actually see that far out in the extreme ultraviolet wavelengths. We didn't really know until we did this experiment. So we see out to 5 solar radii. So what we want to be able to do with JEDI is to, of course, study the extreme space weather events, but also make sure we understand the ground state of space weather. So what the solar wind is doing before these extreme events go into it and how they will then interact. In order to do that, we've got 10 times greater throughput than Solar Orbiter. So with Solar Orbiter, we were obviously, it's in a very difficult orbit. It gets in close to the sun. We were quite constrained in what we could do with that, but we can do things like on JEDI, we can make the aperture bigger, for example, which means in the end that we've got 10 times greater throughput. So this will be very, very cool. I mentioned already, so Don Hassler is the PI. NASA's Living with a Star program office overseas. All of us, and ESA's Vigil project, obviously overseas as well. Nikki as project scientist. And then we have John Andrews from Spheri as the project manager. Matt Beasley as the instrument systems engineer. And then from the European side, there's PBOD in Switzerland. We're doing the detector front-end electronics. And then CSL, ROB are doing the detector door. And we also have IAS doing the mirrors and filter wheel, which is also coming from EUI. So what we want to do is to connect coronal mass ejections to their solar sources and signatures in the corona. So you've got an image of the compact coronagraph to the left, and you'll see obviously with the occulting disk, there's a gap. And we always know when there's gaps, something exciting happens in the gap. And JEDI will fill in the gap basically. So you can see the fields of view here. JEDI field of view is shown with the compact coronagraph and then the sun-earth line. So we'll fill a gap. We'll be able to connect the coronal mass ejections and other structures in the corona to their source regions observed in the sun. And with that, obviously, we'll be linking to the magnetograph, which will be very critical for us to understand how the magnetic field is changing. So the middle corona, on the left is an image from, I think it's figure 1 in Matt's paper, which you should all read. But it really illustrates the complexity in that region. So we're going from the photosphere, which is around 6,000 degrees, and then into the corona 1,000,000 degrees. The changes that happen in that region, the changes in the density, the changes in the plasma beta and the different regimes, so whether you're in coronal hole, whether you're in the streamer belt, the physics is changing dramatically. So you're jumping from what happens on the solar surface, and then something magical happens, and you've got a gap in your data observing, and then you get into your chronograph data. So we want to be able to image that gap, basically, so that we can track things through more thoroughly, which will help constrain the modeling better. We know the lower corona is really highly structured. We see that in the imaging that we've had for many years now. We know it from SOHO and before. We've got 30 years worth of data. We see the structure in the outer corona as well, but we don't know the precise physics of that connection. So the occulting disk on EUI on Solar Orbiter. So this is an example movie. It's the one that Fred published in 2003. So the middle image at this time was from stereo. And you can see the structure in the EUV wavelengths using the occulter, which is it was not being done before, so we can see how highly structured it is. The exposure times on this are about 650 seconds or so. And here's a more recent data from October last year, where you can see especially the flow on the left-hand side. You can see dynamics occurring here. This is with swap in the middle. So the occulter on EUI has really allowed us to understand how this could be used in a more synoptic, consistent way. We don't run it because this is on this data set is oops. No, I can't go back. Sorry, lost control. We don't use this continuously because it's on the door, basically, the occulter. So it was kind of like not a last minute add-on, but it was an add-on to the door that wouldn't disrupt the rest of the way the instrument ran, basically. So and we operated the door mechanism. We don't want to overkill the door mechanism, so we don't operate it continuously for EUI, but the design is different for JEDI. So the other thing that happens in this region, sort of in between, is that you've got different size scale structures. So we know we've got kinetic scales in the solar wind, these small scale features that will heat up the plasma and so on. And we know we've got the large scale structures coming from coronal holes or coming from coronal mass ejections. And then we've got this stuff in between. So this image on the left is work from Craig DeForest, who will join this afternoon, I guess, online. I don't see him in the room. And he did a deep field stereo core 2 observation. And that was in order to show or to demonstrate whether or not there was structure in that outer corona. And they illustrated that the solar wind is full of these mesoscale structures, so from tens to 50,000 megameters or so. So this structure is not smooth, it's not simple, and the more we look in the details of the structure, the more complex we see. So these mesoscale structures are seen in stream interaction regions, coronal mass ejections, and can potentially be more important than the shock themselves. So the solar wind is a direct result of how it's formed. So we see, wherever we look with the imagers, we see outflows, we see brightenings, and we see more and more of them with solar orbiter because we've got such high resolution. But here are examples here on the left. You see the small details, you see small brightenings, you see small jets. You see these extended structures that are feeding into the solar wind. If you look on a larger scale, here you've got active regions, you've got coronal holes that interact with active regions. You've got this complex web of coronal structures around the sun, and we need to be able to see them at all scales. We need to be able to see how they link together. So JEDI is an instrument. Very briefly, the SWOC has these 3 filters, so going from helium-2, iron 12, and then the iron 8, iron 20 filters. So the instrument itself is about 1 meter long and nearly 30 centimeters high or height. And we have let's see, no, I don't point in that screen. I want to see a line. You can't see a pointer. Okay, so we have the primary mirror. We've got baffling to keep out the visible light. We've got the front electronics on either side for the SWOC and EWOC. And then for the EWOC, we have the 2 bands, 2 filter bands. So you can see the filter wheel and the baffles. So we go between these 2 filters. We've changed, this is basically what the full sun imager on EUI looks like, but there's been a couple of changes. So the door and occulter have been moved a bit in from the entrance aperture. The entrance aperture has been doubled in size. So this allows us to get the order of magnitude better throughput that I mentioned earlier. Thank you. So the field of views are shown here. So the SWOC is 77 by 77 arc minutes, and EWOC is 3.8 by 3.8 degrees. Spatial resolution is 3 arc seconds, and then 9 arc seconds, 3 solar radii. What else would you like to know? The cadences you'd like to know. 4 minutes and 30 seconds for the SWOC, and for EWOC, 8 minutes, 1 minute. So that's what we're aiming for. The fields of view you've already seen. So what the timescales for Fidgel are very, very tight, which Matt will express later on. So we're trying to build as much as possible on pre-existing work. So we've got the Silobiter door and occulter is being basically reused. The detectors that we're really be learning with EUI, how to get the best out of them. These CMOS detectors will be used. The filter wheel will be used as well. And then we did work at PMOD on what was Lagrange, and now Fidgel on the front-end electronics. So we're trying to use as much as we can to go as fast as we can to, but the schedule is very tight. Let's see, I'll skip that. So JEDI is has an extended field of view through the middle corona. So this is one of the real goals in our science case of the proposal, was to make sure that we could fill in the gaps. And we're able to observe from the chromosphere the flaring corona. So this allows us to do the connection between the photospheric magnetic field through the low middle corona and then out to C core. So we're looking forward to getting the data from this instrument, and we're also doing other experiments with EUI occulter, kind of thinking of how we would use it on Fidgel. And with that, I will finish.
Thank you very much, Louise. Great talk. We have questions for Louise. Yes. Okay.
Your choice for the IM8 line, the 133. Can you tell us a little bit more about that choice?
So, I mean, this was based on the fact that we want to see flaring plasma. So this allows us to see the hotter emission up to 10 million degrees through the iron 20. So it's kind of nearly focused more on the iron 20 than the iron 8. So that was the reason for that choice.
Scope as well to look at different parts of CMEs and maybe do some composition, constraints on the composition, for example, with these channels and so on.
For the composition, I'm not sure we could do that because the filters are quite broad. So I'm not sure that that would be useful for composition. But we do have the basically SWA on board, right?
But without composition.
Oh, without composition. Okay, sorry, we don't have composition. I thought there was composition. This is why we're all here.
Yeah, that's what I mean. That's right.
Yeah.
Do we have questions online?
It's not really people can actually ask questions.
You probably asked it for anything.
Yeah, but the Q&A.
Or another question in the room? Yeah, Matt, go ahead.
Very cool. It's pretty good. Very excited about it. I think it might be a couple of things. I was originally.
I think you were originally. I think you.
One thing that I think like you covered a lot of this very well, and I would add to it, perhaps talking about stealth CMEs that might be forming higher up in the solar atmosphere. That's going to be pretty exciting. Secondly, have you talked to Ritesh Patel at all about his Optra transform software to automatically detect eruptions through the acceleration?
No. No.
Talk to him about it because
you send me the details. Yeah.
You have a backup to like the campus to automate the detection through and you've got the perfect good use.
Yeah. I mean, I think this is what, because there's lots of arguments on where things are formed, right? And then you've got this gap, and then you don't know where things are formed. So there's all these debates. This is partly why we wanted the hotter line as well, because that can give you an insight into the reconnection events that are happening higher than maybe you think they are. So yeah, no, we're looking forward to that.
Very cool. Yeah.
Okay.
Yeah.
Fidgel is not a science mission. Even right data observations is really good. And it's language.
You're correct. It's not a science mission. And these are the cadences that we will have. So it's 4 minutes for SWOC and it's 8 minutes for EVO. Yeah.
All right. I think we have to move on. Thank you very much again. And our next talk is actually an online talk. We've pulled them forward because they're based in Korea, and we didn't want to make them stay awake on a Friday night on Valentine's Day until midnight or so. And that's about a complementary effort led from Korea And that's the title of the talk is Opening New Horizons with the Korea-led L4 Mission. And I think Roxun is online. If you unmute and oh yeah, we can already see your screen. Perfect. Please go ahead.
Everything is okay?
Very good. Yes.
Okay.
Thank
Then
you.
I will start. Good morning, everyone. I'm Rosun Kim, the scientist in charge of the heliospec imager in KASI L4 team. Actually, the PI of L4 project in KASI is Dr. Kyung-Sok Jo, but he is now on a business trip on the plane. So I will give this presentation on behalf of him. I will start with an overview of the L4 mission and then briefly introduce the development of a heliospheric imager later. As you already know very well, L5 observation provide us with a preview of solar activity. Compared to this, L4 observation provides a direct view of solar source, which are magnetically connected to Earth. With the observations from Earth, L1, L5, and L4 all together, we can enhance our understanding of the heliosphere and also forecast the capability of space weather in heliosphere. There are plenty of benefits of L4 observation. By observing from L4 in addition to L5 and Earth, we can study the evolution of an active region over a longer period and investigate the 3D structures of a filament, prominence, and CMEs. Since we are based on the magnetically connected active region at L4, by monitoring the source region of solar energetic particles, we can expect before eruptions in advance. Recently, humans have started to explore the moon and Mars for journey and future settlement. During this journey, the most dangerous situation might be solar radiation. So monitoring the solar radiation, that is SAPs from the L4 point, it will help predict SAP effects more accurately and more quickly before eruption. This is why L4 observation plays a crucial role in M2M architecture. And if we give some inclination to the L4 orbits, we can see the solar polar region where we are interested in as the source area of fast solar wind. By observing this region, we can study the longitudinal circulation of the sun and the prediction of activeness for the next solar cycle. And we can generate a near real-time synoptic map constructed using multi-point observations from L1, L5, and L4. Also, this kind of multi-point observation can contribute to understanding 3D heliospheric structures, such as heliospheric plasma sheets. And although this is not the main objective, if L4 has a dust detector, we can study the distribution and characteristics of dust within heliosphere, thereby investigating the origin of solar system. These are the milestones, what we are planning. We expect the L4 to be launched in 2035. And as the first step, we are now performing a feasibility study to prepare a proposal, which is to be submitted to the Korea Aerospace Administration, KASA. In this study, we are developing a strategy including science, technology, and international collaboration. We are now this budget estimation now. And from the start, the Korean solar physics and space weather community tried to derive proper scientific objectives and corresponding instruments. Regarding this, we have already published papers on the L4 vision and plan, remote sensing science, and in situ science, and also multi-point observation analysis. And we derived the three main objectives as the science requirements: space weather in the heliosphere, and magnetized plasma structure erupting from the sun, and their initiation and dynamic eruption, and also solar energetic particles and their origin, properties, and propagation characteristics. The keywords might be space weather, CMEs, and SAPs. This is the science requirement matrix. We are continuously sharing this matrix with the scientist community and updating it based on their feedback. Okay, ready? Corresponding to the science objectives, we then selected the payloads. For remote sensing, we are considering photospheric vector magnetogram, H-alpha spectrograph, UV imager, white light chronograph, heliospheric imager, and X-ray spectrometer. Still, it is not decided yet, but because now it's in the initial stage, we want to include all of the possible instruments so far. We expect that the H-alpha imaging spectrograph will be a unique instrument led by Korea. For in situ measurement, we will develop two packages. One is for field measurement and the other is for particle detection. We also included a dust detector, but everything can change. And to achieve our goals, we are discussing our technical capabilities of payload, satellite, launch vehicles, and so on with domestic and international universities, institutes, and industries also. We will decide which elements of L4 should be developed or provided domestically or internationally. This is what we have done so far to realize the L4 mission. And now let's move to the heliospheric imager. And I don't want to talk in detail about HI science, but I should mention that we try to align the role of heliospheric imager with mission science objectives. So the major role of HI at L4 can be summarized like this. What are the 3D characteristics of CMEs, including their geometry, kinematics, and magnetic flux lobes? And how do CMEs evolve and propagate in interplanetary space through interaction with the solar wind and other CMEs? And how do these evolving characteristics affect space weather impact? As you know, we have no prior experience with this instrument, but even if we have, it is very difficult for any single country to develop the instrument on its own. So we hope to develop this through international collaboration. Fortunately, a domestic optical company has shown interest and is willing to join the development. And we have already discussed with the UK, which have valuable expertise from stereo and other mission. And since Italy is now preparing for the heliospheric imager for VISIR, so we are discussing with them too. We are also considering working with Belgium. Currently, discussions are ongoing at the agents-to-agents level by CASA to define specific contributions. So this is the current preliminary design. It follows the specs of instant Felix and the most heap, which were recently suggested. We haven't included the polarization function yet. Further details will be determined in the future. We think it might be good to be modified following visual heliospheric imager for synergy. And to maximize the effect of HI observation, we are planning to build an international science user network. Through this network, we aim to determine instrument specs, establish observational plans aligned with key science objectives, and maximize the utilization of future HI data. For this, we will organize international workshops and regular seminars in the near future. The working group should cover the solar transient evolutions, including changes in the density and speed for blobs, streamers, CMEs, and irregularity of heliospheric current seed. And the statistic studies on CME propagation, such as acceleration, rotation, and distortions of CMEs during the propagation. And also, personally, I have interested in the CME interaction. So, because we can see the direct evidence of CME's interaction in the HI image as shown in this figure, by using HI data as the using this HI data as the input and the validation for the models, we can expect robust simulation models for heliosphere. So please keep your eyes on this and hope you join this network. I will stop here. Thank you so much for your attention. Any questions?
Sorry, we were just on mute, so you didn't hear the applause in the room. Well, thank you very much for the great talk. Are there questions for Roxun? There's one question in the room, and I will repeat it for you. Yeah.
Okay.
A brilliant idea. If I had fish remembered and those fish pronounced too bad, it sounds like an application to the whole world of a traditional cultural ethical principle, which I think is called John.
John, an ethical principle.
Parable character applied to the whole of Korea and now applied to the whole of the world.
Oh, very good. So that's a. Did you hear this, Roxun? It's probably a bit hard to repeat this.
Please repeat again.
It was a comment about an ethical concept from Korea. Is that right? Called Chong?
Yeah.
Chong.
You
Sorry.
mean,
very good. Do we have other questions online? No questions online? Yeah. Just as a reminder, if you have questions, please put them in the Q&A online. Okay.
Okay.
Any other questions?
Yeah.
Yes, Matt.
This may be a question for Tim or perhaps Jackie, I'm not sure. It's going to be very interesting. HI instruments at L5 and L4. Unlike the chronographs, where we're kind of in the small angle observation, we're going to be looking at emission from constant surfaces from different perspectives. Are there any tools out there, perhaps during the scenario days, there are, Jackie's nodding her head here, fantastic, for modeling eruptions as they move.
Could you repeat?
No, hold on. It's a bit difficult to have a discussion like that in the room. There was a question about the existence of tools that can be used for heliospheric images together at L5 and L4 if you have two instruments. And I think
Actually,
already there was a comment in the room that we already have a lot of tools, but maybe you want to
yeah.
comment on that.
Yeah, we also will start some kind of AI study to construct 3D image using multi-point observation. So that should be considered. Yes, definitely.
All right. Very good. Let's thank Roxoon again.
Thank you.
Thank you.
Thank you.
We'll come to the next talk. And I think that's Justin's talk, an in-person talk. We have the slides here. And the topic is the space weather prediction pipeline for real-time heliospheric imaging data.
I'll do it as fast as you can.
There's the third one, yeah. Cool. This talk doesn't work. I'll give you a sign.
So good morning, everyone. I'm Justin Luedek. I'm a postdoc at the Austrian Space Weather Office, ASWO for short. And as we were talking about HI just before, going straight back into it. So I'm going to introduce some tools and results we got from the Space Weather Office using HI data, and specifically about the predictions around CMEs and the arrival time and arrival speed and stuff like that. So 3 of us at ASWO are working with HI imaging. So there is me, Mike, and Tanya. So all 3 of us are working on different things that's part of the project, but all around everything centered around HI. So Tanya is working around, I don't know, that's the question. Oh, yeah. So Tanya is working on the drag-based model, which has been there for a few years already. And this is tracking CMEs in the HI field of view. So using different points tracked around across the field of view and doing predictions with that. I'm working more on the data side, so the post-processing of the data and trying to make use of previous missions, the stereo mission in particular, and the beacon mode of this mission. And finally, Michael is working on the automatic detection and tracking of CMEs. So trying to make a nice tool that facilitates the tracking of CMEs, some alert system, and some nice predictions out of that in the future. So starting from Tanya's work, which is about CMEs and using this drag-based model to predict arrival time. She recently worked on trying to assess what is stopping us from using that and getting good performances with that. And with another scientist, tracked different CMEs and looked at how long do we need to track them within the heliospheric field of view, to get accurate predictions. And also how much of these points and missing data and data quality, how much does it affect the predictions. And so doing that over like 15 TMEs and comparing the tracks between our tracking and another scientist tracking and reducing the track length to a minimum as possible, around 10 elongations, the maximum around the maximum of HI2. She got to the conclusion that, as we would expect, the longer we track, the better the results are. And in particular, if you look at the fixed by fitting, which is a method to get the speed and direction of the CME using these tracking points, you need as many points as you can, which is sometimes a problem because of the data and the broadcasting of the data. So this is that, and also the more you have points, the more precise you are in forecasting your CME arrival, which also makes sense. But out of this study, 2 main cons came out. The first one is that you need lots of data points. So if you miss data, if you have data gaps, if you have bad images where you don't see CMEs, if the CME becomes too faint and stuff like that, then it becomes very hard to track it. And then your predictions really suffer from that. And the second point is that it's very hard to have consistent measurements between scientists. 2 people who've been there for 20 years tracking CMEs will have very different predictions. And this is something that is hard to get on the same level with everyone. So coming out of these 2 points, I'm going to talk about the first one, which is the data side, and then the second one, which is the tracking part. And about the data part, we come into the beacon to sense part of the presentation. So it comes from the stereo A data, which has 2 modes of broadcasting the data. So it has normal mode, which is science mode, which because it's a science mission, which shoots images at a quite high resolution with a quite high cadence of 40 minutes. However, the data is broadcasted 4 days later, 3 to 4 days later. So if you want to do any forecasting or any real-time predictions, then it's basically useless. But there is very limited data gaps as we get most of the data on Earth, and this is quite good quality. On the other hand, you have the beacon mode, which is a near real-time mode, sending data as soon as it is captured on the spacecraft. However, it has a very low cadence, so every 3 images are sent to Earth. Because it has a very low bandwidth compared to other imaging devices or data, then data is very compressed down to 256 by 256 pixels. It is quite a lot binned as well. So the quality of the data suffers a lot from that. And because of this broadcasting problem, then you have lots of data gaps. So you're missing lots of images, and sometimes you have some days with only 1 image or even no image at all. So this is one of the main problems of the beacon data. But if you want to use it and do real-time forecasting with that, what can we get out of that? So the goal is to use machine learning and try to improve the quality of the images. First of all, their quality, so denoising them and upsampling them, so getting better resolution, better visibility of the CMEs within them. And then the second part is getting a higher cadence. So trying to interpolate between images so that it gets a bit easier to follow the CMEs through the heliosphere, track them, and distinguish them when there is some interaction, as previously mentioned, or just to get a better idea of how they move or they propagate. So both of these are machine learning based. I will not go too much into details, it will take too much time. So we can talk about it later if you have questions, but we see some results later on. So in terms of metrics, which is the boring part, you get quite good results. It shows that we can get quite good images out of that, even though the starting quality is quite bad. We can get high quality images with very much less noise than we got at the beginning, which is quite promising. But what does it look like? So in terms of enhancing and denoising the images, it's playing nice. You see on the left, you have the beacon data. On the right column, the science data, and in the middle, the enhanced version of it. So the noise levels are quite reduced, and you can see much more of the details of the CMEs. So we're not. It's much more clear where the front, or at least the leading edge of the CME should be, and this makes it way better for a human annotator to follow the CME and track it. For the interpolation, similarly, on the left, you have the first image, the first beacon image, on the right, the second beacon image, then the 2 enhanced versions of it in between, and then the interpolated images. As you can see, it works quite well, and it doesn't invent anything, and it kind of reproduces the front of the CME and the important features and propagate them within 2 images, making them quite smoothly and nicely to follow. But how can we assess that? The idea would be to track such features and see if the track makes sense at all when we compare them to the sense data, which is the high quality data. So for that, we built this kind of like nice little tool. So usually we track CMEs within the J-plots, this kind of time and elongation plots, where you have this streak of lights that corresponds to important feature propagating and associating them to like a CME. It's supposedly core or front, then we can track them. But you lose the context of what is actually in these J-plots and where the CME is going and what you're looking at. So that's why using the images as well is kind of important. So we combine both of them, where we have on top of the image the CMEs themselves, the 4 images, which are upsampled and enhanced and interpolated. And at the bottom, the J-plots. You have the correspondence for all the images, where your mouth is, where you look at, what the ecliptic is, and where you should track your things to forecast them and predict the arrival time to Earth. So from that, we track in all the 4 types of data: beacon, the enhanced version, the interpolation version, and the science version. And then we compare everything to science. And this is kind of the error of the tracks compared to science. As you can see, beacon, even though it's not too bad, you have lots of divergence in what you track for lots of CME events. You tend to track the wrong thing, get completely lost in the images and the J-plots, and end up with completely wrong track and wrong dynamics. While if you look at the enhanced version, the interpolated version, then we kind of get quite good compared to sense, which makes us believe that it's a good alternative to use previous missions data, even though it's not perfect for real-time forecasting. And this is the conclusion for this small part. We've reduced the noise and increased the spatial and temporal resolution of images using the beacon data, which is quite nice. We improved the tracking for these such features. How does it translate into forecasting and prediction model? We don't know yet. That's another problem, but the tracks themselves are quite better. The last problem that we have are the data gaps. We cannot do much about it because it's just missing data at this point. Maybe including different viewpoints such as coronagraph and other missions from different view angles could help, but this is things we need to investigate. And the last part of the presentation is about the automatic segmentation and detection of CMEs. So this is also using machine learning. This is Michael's work. He worked on segmenting CMEs and using this kind of like neural network architectures. The goal of this part is to get this kind of nice segmented front of the CME so that we can track them and then do some predictions out of them. It's using a neural network. It's kind of like classical 3D autoencoder neural network. Why 3D? Because there's this temporal aspect to it. It's not just single images. It's sequences of images so that you have this temporal context and you know what you're tracking and looking at. We've spent quite some time annotating images. So as you could see at the bottom in this nice video, like these fronts are annotated, are painted over. So we identify them. We use different catalogs such as Hellcat to get their starting time and where to look at, which direction, for example, like which position angle, which elongation and such, and then annotate them. And this gives us about a bit more than a year of data. It was quite long to do. However, around 50% of it are composed of CMEs. We use the classical testing and training split for the neural network, and we use sequences of 16 images. So with that, we get quite some nice results. This doesn't look so impressive at first. You're judging by the size of the segmented front, but the results are quite good. They are not perfect. They are always far from an expert doing this kind of job, but they are really fast. So this can be deployed in real time, and we get nice segmentation and prediction of the CME leading edge. And even though we have a low false positive rate, we still have some false positives. But by looking at them, sometimes they still look like CMEs and some events which may have slipped out of some catalogs. So it could be like a good tool to also get other events which were missing from previous catalogs because uncertain to find or too difficult to analyze. So in summary, we have this nice automatic segmentation tool, which works on temporal information, and it's still challenging data to work with and challenging task. And this was on science data, but future work will be about how to integrate it with other missions, evaluate the tracking capabilities, not just segmentation, and also see if we can use the beacon sense as an input directly for this method. Yeah. So as conclusion, we've offered like kind of 3 different blocks as part of our pipeline. 2 of them are machine learning based for improving the data and also improving the segmentation. And also we saw that drag-based model and kind of like this kind of prediction tools using edge-like data are working quite well, but they are highly dependent on the data that we get. So hopefully with Vigil mission in the future, we get some nice, continuous and relatively good quality data that we can use for such purposes. All of this will be in some 3 different papers, which will be submitted soon, hopefully. And at future work in short term, we need to validate everything. So applying that in real time, spend some time tracking things, predicting things, and seeing how does it work in the future. And also long-term Vigil coming in 7 years, 8 years, and maybe the information, as mentioned before, could be nice data sources for such methods. And that's it.
Yeah, thank you very much. Do we have questions for Justin for his talk? Jonathan.
How fast does the beacon to science pipeline take? How fast?
So
we have to repeat the question quickly for online. Yes.
So how fast does the beacon sense, does it work? And how fast does it work? It's quite fast. I mean, it's like milliseconds per image. It takes a while to train, especially because we used 15 years of stereo HI data, so it takes a good few weeks to train. But once it's trained, it works extremely fast. And we deploy it now on our server, and every 2 to 3 hours, we just run it and get nice JPEGs, nice images out of it. So now it's just a matter of letting it run, basically.
We have more questions? Matt?
Sure. This is really interesting. And I think that you also very interesting how the L4 machine as well.
Yeah.
So when they were running. Does the model take into account the Thompson circuits?
So not really. So does the model take in consideration Thompson surface? So no, it's purely data driven for now. So for example, the interpolation part, we want to introduce physics into it because these are physical objects that we see propagating through the heliosphere. So adding more constraints to it will make it better. But for now, no, it's purely data driven.
Can I ask a quick follow-on as well?
Well, maybe we move this to the discussion, or while we switch over the presentation, maybe you can ask while we switch over. Yeah. Okay. Well, then let's take Justin again. And nicely connected also to the previous talk that we had, and we stay with CME because the next talk is by Siegfried Gonzi about CME onset characterization from L5.
Something has happened to. Oops.
Oh,
Sorry. Is it,
where's Siegfried? There.
I do not know what happened.
Is that okay, or is that has it messed up everything?
Vice Pro. I apologize, but are you using a Macintosh?
No, it's
No.
easy. You can join the meeting.
Are you on Zoom? Are you on the Zoom?
No, the problem is I have the same problem on my MacBook.
Ah,
Oh,
Okay, I did it with PowerPoint, but I apologize. I hope it's okay.
do you just want to give it a try? We'll see how it goes.
Yeah.
All right.
If you could the point, that's fine.
No, not for the online people.
so this pointer is just use them.
That's okay.
Okay, so how do I go?
And when you press that, go forward.
Okay. Hello. I'm Siegfried Gonzi from the UK Met Office. Hope everyone can hear me. So I wasn't sure actually if someone is presenting our ESA project. So obviously not. So I really apologize. So we were tasked. Okay, ESA asked us, can we actually show the other benefit of an instrument or spacecraft at L5? It's actually a big project. I only show a small part what I did. So, okay. So we know from experience that the multi-viewpoint instrument will definitely give us a better fit when we fit CMEs. So we know this especially by using the stereo spacecraft. So you were going to learn a little bit more later on the slides. But if someone really asks you, can you actually demonstrate it? It becomes really difficult. Now for this ESA project, we analyzed 15 CMEs. Why did we do it? So in 2009, 10, 11, and 20, and 21, the stereo spacecraft shown on the slide was approximately at the location where we sent the spacecraft to L5. So the good thing here is we actually could use real data, so we don't have to make up data in a data simulation experiment. We definitely can show that the chronograph will help us at L5. Because if you only have one viewpoint at L1, you always run the risk that you misfit the CME. Okay, there's no cutoff here, but it became very difficult to show that we can really decrease the arrival time error of the CME at Earth. So this is the CME analysis tool. So when you visit the Met Office and walk to the forecaster room, you definitely will see a forecaster sitting in front of a computer, and one screen has the CME analysis tool on it. Now, we are redeveloping the CME analysis tool. If you want to learn more, Anders is here, he's the expert. So, but anyway, so what you see here is in the CME analysis tool, we see an image, a chronograph image from LASCO, from L1, but you will also see another image from the stereo instrument. And the forecasters use this over distance and time here. So images come in at the fit point. And what you then get here is the latitude, longitude, the count angle, and the initial speed of the CME at 21 solar radii. So these are the boundary conditions from the CME. And this goes then into the Sun to Earth model. So forecast is the right 4 parameters here. Okay, I made the point earlier. So in 2010, the stereo P was approximately 60 degrees here at L5. Now, what really would help if you had the spacecraft just at L5? Because, so this was from 2 days ago, where stereo B and stereo A, because the stereo spacecraft moves around, right? It's not always at the same location. So 2 years ago, stereo was lined up with L1 then it's less helpful in the semi-analysis tool.
Sorry to interrupt you, but I think we found an option to show the slides in the right way. Is that okay? But you just have to tell us when you want to go to the next slide.
Yeah.
But I think Jonathan can project from his computer. And then we should see, I think this is a bit easier than this.
Yeah,
Right?
yes, it was. Yeah. Is it big enough? Okay.
Okay, so now we change.
Okay, you are going to the next one. I come to, okay. So these are the 15 CMEs. This was officially signed off by ESA. So, and this were the experiment. I mean, I can't go into the details here, but the experiments one was just, if you just use the instrument L1 into the CME bit, and then the arrival time forecast, and then you add the chronograph from L5, in this case from stereo. And also we added then the heliospheric image and card in the CME analysis tool. And also we had, I mean, ESA actually asked us what we think would be a good cadence and resolution of the instruments. I don't know, Jackie can maybe later tell more. The thing is, it's actually quite, the problem is in terms of resolution. We also had an experiment where we reduced the resolution. The CME analysis tool, you won't see much of a difference between 1000 pixels and 512 because everything is cropped in the monitor. So actually what you probably would need is really a big screen like this and to get pixel for pixel. And also the cadence was not as important as we first thought it is. Cadence here means an image comes in every 30 minutes. Okay, this gets a little bit messy. This is quite an interesting plot for me, actually, because we had 3 MOSWOC forecasters. They are professional forecasters. And all those MOSWOC forecasters were fitting the same CME and for all 5 experiments. Now, we can't analyze every CME here. But what you can see, let's say CME number 2 here, and the blue dots, this was experiment number 2. This is actually what's being used at the moment. Currently at the Met Office's operation setup. Now you will see 2 forecasters, the longitude of this CME, they fitted the longitude approximately at minus 15 degrees, minus 20 degrees. But one forecaster fitted the CME plus 70 or 80 degrees. So this CME will never arrive Earth in the model. But we know from those 15 CMEs that all the 15 CMEs were Earth directed. So you can see, even without running a model, just analyzing the CME, there's a large error involved in this business of CME fits when you use the CME analysis tool. And green overplotted here, I think Volker is giving a presentation in the afternoon from the cylindrical graduated shape model for experiment 2. There's a different way how you can derive those parameters at 21 solar array. Instead of using the CME analysis tool, use something slightly different. Now the problem here also is we don't know the grounding truth because, I mean, already we know they are Earth directed, and this means the longitude at least should lie between minus and plus 60 degrees. But we don't know that, we haven't got the grounding truth here. So this becomes, no forecast is wrong here, actually, to be honest. So anyway, so these are the 15 fits because they also fit in a lot of other little bits of the project that people use those CME fits. Now, how did they arrive in the arrival time at Earth? Actually, this is the same way that the forecasters did the Met Office, although they have a lot more experience. Also, when you go to the forecast room, you will always see a screen with the sun to earth model. You get a 5-day forecast here of the solar wind speed and the density. This is the movie, then wouldn't work here, but then you see the CME coming out here and coming down to the earth. A top-down view, the side-down view, from the length we get the velocity, speed. But also what we use at the Met Office is an ensemble system. Because often it becomes quite difficult to derive the arrival time just by deterministic forecasts. Because we know there are so many uncertainties, right? What you also then use is the wind speed and the density. But the overplotted here is the observation. When they do the forecast, they wouldn't have those observations because it's a 5-day forecast. So for this, I think this was in E5, this was the arrival time. What we had the official arrival time and the sign of this ESA, and this would have been the forecast. So and I then literally eyeballing. You look at those plots and say, hey, the CME has arrived this and this. I mean, everyone would do it slightly different. You can argue if the CME arrived here. I had it already arrived in the first ensemble member somehow else as well. So I used then these kind of plots derived for each experiment and for each forecast the arrival time of the CME at Earth. So actually remember, the idea actually was to show or demonstrate that we can reduce the arrival time by using an additional instrument at L5. And first, I think, but this was completely unrealistic. We thought we can then reduce the arrival time. Okay, when you go to the NASA scoreboard, arrival times are often wrong by a whole day. On average, they are good, they're 12 hours or so. But the ESA then asked us, can we then show it if you reduce the arrival time, say, down on average to 6 hours? I don't think you can show it actually. Again, so these are the 15 CMEs here. Experiment 1, 2, 3. The last one, the last plus L5, and the last plus L5 with the heliospheric imager. Then each row here for forecaster 1, forecaster 2. So we can't go into the detail. But this then, this is what you would get when you stick those CME fits into the model and calculate the arrival time. No. Okay, what's actually shown here, and then there's another slide this. What we actually can show is, for example, CME number 1. This was a very difficult CME. And if you only have for L1, the arrival time there is quite large. Then if you include then the L5 instrument, you also can then reduce the arrival time error because the fit becomes more sensitive. But you can't really show that those errors here actually go down once you add the L5 for images. I mean, because the error in the initial fit is so large. Because we couldn't really convincingly show, but there's a slide where I think L5 can help us, that the heliospheric image will also reduce the arrival time. Because the problem is, the CME analysis was never written in a way that you include the heliospheric image. So I included it then for the forecasters. But they obviously didn't really like it because it didn't help them with the CME analysis. Because the idea is once the CME moves out from the chronograph, say from stereo, then from L5, then it moves into the heliospheric imager view. It will help you constraining the fit more, but it's not trivial. Yeah, so I need to skip. Okay, so we skip this one here actually then. Actually, I got this directly from the report. I actually forgot to produce those tables. But what we can show is here. So the mean error, the timing error, just if you use the instrument as alone, it's typically 11 hours of the arrival time. And once you start using the L5 chronograph for the CME analysis and then run the model, you can, okay, these are average. So they didn't do a standard deviation. Can reduce an average arrival time, and it can show it. This instrument definitely helps in reducing the arrival time error. So this was a brush-based model, and other team in the project used my CME fit with the forecasters produced for their model. It's a similar thing. Also for the relative shape model, you also can see this is for experiment 2. You use the arrival time error. Once you start using adding the instrument from L5. Although the project was a lot bigger than I just showed you there, it's like, okay, what I think is going to happen then once we have got the virtual machine is the magnetogram. Because at the moment we use the magnetogram from the ground global oscillation network group. Because the idea then is you have got another few points and you stick those magnetograms together because the synoptic maps, they have the error in those synoptic maps is quite massive. I didn't show you this error, but this is actually, this goes in the background boundary condition, how you drive your model, and then the perturbation of the CME goes on the top of the model. But this error is massive. So you can probably reduce the error in the synoptic map of the line of sight of the photosphere from magnetic field. Also, there was something in the project of a data assimilation, because you can use solar wind observation from L1 and L5 to go back to the initial boundary conditions at 21 solar radian and try to improve your background state. So it gives you a more realistic initial state when you run your sun to earth model. And also actually redeveloped. So we also need to think how we can better include the heliotheric image and the CME analysis tool. Because at the moment, when the forecasters start fitting a CME, they start fitting the CME in the chronograph from L1 and L5. And when they see then the CME front in the heliotheric image, often this fit doesn't really line up with the chronograph fit. And in the CME analysis, you really can't go back and forth. You can't adjust your fit. So yeah, I apologize again that no one has given you an overview of the whole project, because it's quite difficult probably to follow what we did, but it was a big project. And we learned a lot, to be honest. We really learned a lot. It's like, but the thing also is you have to be realistic. This is, okay, we have operational forecasting center. And then the ESL5 mission, we built upon the existing infrastructure that we have now. We are not going to then change how we're doing space weather forecasts with L5. We built on existing tools, the infrastructure of what we have now. So I mean, that's an ESA report if someone is interested in, right? It's now released, Chucky, the ESA report, if someone wants to learn more about the whole project. Because it's a big report of all. Then
in the least paper.
All right. I think we have time for one quick question, because then we have to move on to the next talk. There's one in the back. Yeah.
I think this is very interesting because we're actually using the actual forecasters. But your final statement saying that for visual we have to use the existing infrastructure, I think that's a very limited statement, because your study is showing that you actually need to change the existing.
No, but by existing, I mean we can't deviate too much from your already existing one.
I agree.
It's not. So we still have to use the CME analysis tool. Yeah, exactly.
But it does need to.
Now, definitely, the heliospheric image is one new thing. It's like we could also using it for pruning the ensembles. You know, with those stripe plots, this kind of definitely. But I'm making the point is we will still be using the CME analysis tool, for example. It's not like we're using completely something different. So.
Very good. Let's thank Siegfried again. Okay, thank you. And now we're moving on to another aspect of space weather, solar energetic particles with Timo. So Timo Leitinen will talk about forecasting solar energetic particle events with L1 and L5 coronal mass ejection observations. Let's give it a try, otherwise.
Yeah, maybe try the same thing. Oh, it looks like it's just check.
Is it okay, or are we missing? Oh,
Oh, it looks okay. The first slide is a bit of.
Sorry if technical abilities are.
Pretty much out.
I'm sorry, I haven't seen it, so.
No, I know, exactly.
what was it? Yeah, once we set this up.
Degree, you said, I didn't use the right, I know, down to 3 or 5 dollars. Is this not the, is this not the mean error with positives and negatives compensated?
Yeah.
Change.
You come here for the answer, because otherwise they don't hear. Sorry.
Okay, I didn't produce the table, I just found it yesterday in a report. Of course, you're right. This is the thing why I really don't like those mean average errors, to be honest. Because in the end of the day, like it's with a weather forecast, as an end customer, it doesn't help you much because the error can still be 12 hours, 18 hours. But there's a clear trend that you can show the error goes down. This is in all the statistical studies. I mean, I don't know who produced the plot for the report. I think you should have shown also the standard deviation, or yeah. It's definitely a valid point, to be honest. I'm not saying that every forecast now has an arrival time error coming down to 3 or 4 hours, to be honest. It's like, no, yeah.
Okay, thank you. Thank you for clarifying that. All right, now, this is working.
Yeah, I think so. But apologies for the fonts. I really need to check what's going on, but the other slides look okay, so I think we can continue. Okay, so I'm continuing with the actually same project that Sigrid was talking. So the ESA project, we were part of that, and we were looking at how solar energy particle events could be forecasted better using these L1 and L5 CME observations. Just to focus, yes. Okay, it's a bit heavy on the text, but I think we can see. So just to give kind of an update or reminder about solar energy particles, we know that during solar eruptions, we tend to see these increases of relativistic ions and electrons, and then these particles propagate to Earth and cause space weather effects. They can cause satellite damage, affect astronaut health, and also disrupt high latitude aviation. And we know that these particles are accelerated in flare processes, in coronal mass ejection driven shocks. Details are still something that we are trying to understand a little bit better, but that's kind of the idea. We know that there's some correlations between the CME properties, flare intensity, and the CP event. What makes things a little bit troublesome is that because these are charged particles, they are propagating guided by the Parker spiral. I say along, it's not quite along. So that affects on how we see an event, for instance, which is on the western limb of the western side hemisphere of the sun. So we see a very sharp rise and then a slower decay, and more central and more eastern events start to get a more gradual increase and gradual decay. It's not quite as simple as that, but that's kind of the general idea. Then the solar wind is a turbulent environment. We have magnetic field turbulence, and that scatters the particles. And the particles also spread across the magnetic field line because of the fluctuations and also because of the large-scale drifts and corrotation effects. So there's quite a lot of things happening from the sun with the eruption to 1 AU. So predicting these events is not quite simple. So what we can do is we can use models to look at the transport from the sun to the Earth. And that's what Mike Marsh did at UCLan in 2015. Yes, it's 2015. He used our test particle simulation code, which includes some of the important physics of the particle propagation, not all, but some quite important ones, and created a forecasting model
called sparks that then can forecast the SCP events. Sparks uses flare data over M1 class flare, so the location, the intensity and the timing, and then takes the peak intensity and uses the Dirksen's paper where we have a relation between the flare intensity and the peak intensity of the SCP event. That is fed into the simulation. I'm not going to go into detail how it's actually done, but in principle, we use then the simulation data to generate these synthetic event, the darker curve here, and then that produces us the forecast. In this picture, the lighter curve shows the time, shows the actual event observed by F in this case at the same similar energy range, and then if the event, if the intensity and the simulation increases above a certain threshold, then we get a warning, and this alert can be done in a couple of minutes. The flare data is coming in real time, so this is really an operational system, and it is in the, if you go to the ESA space situational awareness sites, you can see the alerts there. One thing that was decided for Sparks was that we have a fixed source size, so kind of the CME size, which came from Webb et al. Paper. Average size of a CME shock 48 by 48 degrees, and that's something that we can look further in this ESA project. So in our new project, we looked into how L1 or L5 plus L1 data can improve these forecasts if we get the source location and the width and also the CME speeds from CME analysis. Siegfried showed the forecasts from the analysis of the CMEs as done by the Met Office forecasters, and that's essentially what we used for the 15 events, which were mainly from 2009 to 2010. Trouble is that some didn't really do much in 2009, 2010. So out of those 15 events, there actually were 3 events with SCPs. So we did more analysis, so the forecasters analyzed a couple of more events, 5 to be precise, that had SCPs, so we had 8 events in total. So it's not a big statistical sample, but it's more than 3. Of the 8 events, 3 events actually had a flare that was smaller than our threshold. So the original sparks that required larger than M1 flare would produce immediately a false negative. So we had a certain, we had a set of, okay, let's cut a little bit. We have a set of tests that we ran. We used the original sparks, and then we looked at if we have CME data from L1 only, or if we have CME data from L1 plus L5, and looked separately at the fixed width and the data from the CME analysis. We also used the flare location or the CME location. That's written down there. Sorry about that. Okay, so looking at the results, I'm going to move this one a little bit because all of them are going to be there. Okay, so what these figures show is the forecast error for the 8 events that we have. The red cross is the original sparks, and then the green and blue are L1 and L1 plus L5. And the top panel uses the flare location from flare, and the bottom one location from CME. And you can see that the red one is not quite as good as the blue and green. And if you look at the statistics, you can calculate the accuracy, standard deviation. You see that the best accuracy seems to be from flare location and L1 CME width, which is a little bit strange. Why not L1 plus L5? The reason is that you can see that some of these events are very good, very well fit, and some others are not so well. bit. And if we look at these events a little bit closer, two of the events are have a very slow CME, less than 500 kilometers per second. And the thing is, those slow CMEs very rarely accelerate particles to higher energies, which means that the Dirksen study that we use to relate the CME speed and the intensity is not really reliable. So we don't actually have enough statistical reliance on the intensity scaling for those events. Okay. Two events were Eastern events, and that's where the something that we haven't implemented yet in Sparks, in the underlying particle transport model in Sparks comes into play. Something that happens later during the event is cross-field propagation due to turbulence, and that will affect quite a lot on the particularly Eastern side events. So Spark at the moment is not very good at forecasting the Eastern events. So we can drop those events from our analysis, and yes, I'm aware that 4 events is not a large statistical sample. But if we look at those 4 events, then we can clearly see that L5 plus L1 gives a better, gives the best forecast. Here, the accuracy goes down to 11 minutes. If we are looking at the this table, otherwise we see that the width from the CME analysis is quite important parameter compared to the just having a fixed width. We can do a similar thing for the peak times. I'm just showing the statistics of 4 here. And here the L1 CME information gave the best accuracy, but because our sample is really low, we have the large standard deviations. We did the t-tests that showed that any CME information is improving about the same statistics. We looked at the duration. The duration is tricky because duration can be very long. Sparks gives a forecast up to 8 days, but if the event continues longer, or if the forecast looks like, okay, the intensities are continuing above the background level and then our forecast ends, we can't really say anything about the quality of the forecast. So we got only 1 flare event and 3 CME events, so we are really cutting the statistics very low. And the accuracy is poor, and this is again due to something that we want to improve in Sparks, the cross-field propagation, because that really affects the duration forecast of the simulation. So here's a summary. I'm just going to skim over we got best results with the L1 plus L5 data. L1 data was quite good as well. As for the outlook, the one thing that we noticed that is that all CMEs were wider than the 50 by 50 degrees, so that might already give a good improvement. Low statistics is a problem, and yeah, it's really a big problem. There is something that we might be looking into the year 2013 when stereo A and stereo B were behind the sun at about 60 degrees. So that should be better because it was more active region, but active time. But that's something that needs to be done. And really looking at the adding physics into the model as well, which is something that we are working now with Damini, who's here. Thank you.
Very interesting work. I think let's start with an online question. We have one in the chat.
Timo, did you look at the potential to improve the SCP peak intensity prediction in cases of radiation? Cases of radiation monitoring L5 better connected with the
No, that was not part of the project. That would be an interesting thing to look at as well, but we didn't do it within this project.
All right. Questions in the room? Oh, sorry.
It's really interesting, right? So I know your statistics are low, which is difficult, but if you use the CMEs and the flares together, so but if there's a gradual or possible event, does it make a difference to your predictability?
Repeat the question. There was a question of, does it make a difference if the event is gradual or impulsive? I think all the big events tend to be more of a gradual nature, so more related to the both flare and CME. That's one of the big debates that we have in SCP community. What is the relative contribution of flares and CMEs? Yeah, it is a very interesting question. Because the flare and CME, I showed you the statistics, and you can see that the error bars are very large for the particle intensity. So the scales are logarithmic. So if we have certain class flare, then we have a certain peak intensity, but these error bars are huge. So if we have both flare and CME information, that should, in principle, improve the estimation. Sure if I actually answered your question or figured out a new question for me.
Thank you, Timo, for now.
Thank you.
And we come to our next talk, which is another invited talk by Hugh Morgan. The benefits of an L5 coronagraph for solar, wind, and CME science and real-time forecasting. So yeah, again, this is not really working, but I'll give you a time.
Okay. Well, I've got my.
Oh, you get your own. Okay, even better.
To the second.
Absolutely. Okay.
Okay. Thank you. So my title is a bit misleading because I don't talk much about L5 and Vigil, and I'm talking a lot more about the solar, wind, and CME forecasting based on coronagraph data only. Oh, wow, it's changed the font and everything.
All right.
There we are.
Everybody's
Okay, so there's my content. I'm going to talk about the SWEEP project, which really brought me into closer to operational space weather forecasting, then focus on my elements of that, which was tomography for solar wind forecasting and automated CME detection. And then I'll bring in the Huxley model, interplanetary model, and then bring in Vigil and machine learning. So SWEEP was the space weather empirical ensemble package, a collaboration with Matt Owens at Reading and Anthony Yeats at Northumbria. And we were to develop a space weather forecasting tool for the UK Met Office based on solar observation and also based on our former research expertise. But it wasn't a research project, it was to develop operational tools. So I'm not going to spend too much time on this, but this was the idea for SWEEP. We've got multiple sources of input data. So we've got solar photospheric B field measurements and coronagraph measurements. And then these feed into various modules that provide inner boundary conditions for the solar wind model, which was Huxley. And then I'm going to focus on my expertise for this whole package was coronal tomography and the automated CME detection. So currently for forecasting the solar wind in general, you're observing the photospheric magnetic field. You've got some model that range in complexity, but they're modeling the complex structure of the inner corona.
And then somehow you're converting that magnetic information from the model into something like solar wind speed, okay? And then the outer boundary of that model feeds your inner boundary of the solar wind model. And typically NLIL is used, a full-blown MHD model. For SWEEP, we aim to use the tomography of coronagraph data as a new inner boundary for the solar wind model. So we take white light observations of the solar corona. You need half of a Carrington rotation time period. You need data over that time period to create a tomographic reconstruction. You don't need a whole rotation because the coronagraph is observing past the limbs. So whatever you see on the east limb, you'll see half a rotation later on the west limb, and you've got a whole coverage of the corona. So there's a lot of data processing. I'm not going to go into that now. Inversion technique based on spherical harmonics. And then for space weather purposes, we reconstruct the density on a spherical shell situated 8 solar radii from the sun. And the movie there is showing a map that is updated every day or two over the course of a couple of years. So that's giving us the plasma density, but for the solar wind model, we needed velocities. So that was a whole PhD project in itself. On the left there, the top map is showing the electron density, and the lower map is showing an empirically constrained velocity. And to do that, we took around 20 years of in situ measurements of solar wind velocity near Earth. And we took the equivalent period of tomographic density maps near the sun. And then we did an optimization statistically between the two. So the base velocity is given then by this equation, which is coming up very blurry there, but hopefully on the other screens. Anyway, it's an empirically constrained relationship between the rho here, which is the density, which is giving us the base velocity at 8 solar radii for the solar wind. Then if we take Parker Solar Probe velocity measurements over the whole Parker period, we get this, this distribution here. And we make the assumption then that whatever velocity you have at 8 solar radii at the base of your model, that then sets the subsequent acceleration towards Earth. And that gives the lower equation there. So given those equations then and the tomographic density, we can then make predictions for the solar wind velocity at Earth. And that's shown in blue here over the course of 3 years. And then the black line is the omni measured velocity. And we actually have very good performance, compares well, if not better than some more advanced models. And because we have densities in the tomography maps, we can actually use a mass flux constraint. So we have densities at the base, we've got the velocities and acceleration, mass flux constraint gives the red line there, which is the densities at Earth from our model. Of course, it cannot model everything you see in the observations. We don't have a, this is not an MHD model, or it's more of a ballistic mass flux constraint, but it's doing quite well. So summarizing the solar wind forecasting, we can provide inner boundary conditions from coronagraph data alone. We don't need the photosphere. The tomography is based on observations at 8 solar radii, so we're avoiding modeling that complex non-radial inner corona. We only require half a solar rotation of input data, whereas to observe the whole photosphere, you need a whole rotation, and we can give densities, velocities, and acceleration.
will this replace magnetic models? No, of course it won't, but it's complementary, I think. It's an independent that can work alongside the magnetic models and provide an independent comparison. That gives robustness. If an instrument has a data gap, then you can use one or the other. So Siegfried has covered a lot of this in his talk, but the current forecasting framework for CMEs, and it's showing the wrong images, which is really strange. Anyway, that should be a coronagraph image of a CME on the left. And then those are fitted manually using the CAT tool to a cone model. So a simple geometric shape fitted manually to a CME image. And then that provides the parameters Siegfried was showing you can give to NLIL, giving the forecast data. For sweep, we aim to develop a fully automated system. Those bottom images are showing coronagraph images from C2 and C3 and Core 2A beacon images. And really with this project, it's a monster code. The devil is in the detail. There's a whole thousands of lines of code just to clean the data, especially the beacon data, filtering noise, removing backgrounds, flattening the images, and also there's a filter that applies a kind of a deconvolution step that separates the dynamic events from the background quiescent structure. And those are the colored segmented regions there. Those are the CMEs. Then the outer edge of those structures are fitted automatically to a cone model, giving input suitable for a solar wind model. So on the top right, we've got longitude, latitude, and for this particular CME, the location and size is estimated as that red circle. And we also get speeds. So the size, location, and speeds are kind of fitted all at once. You don't do a set of images at a time because the coronagraphs tend to be observing at different times. So you do an optimization over a set of images. So the system works. It's been running now without crashing for around 3 months. But there are huge problems with this. And the same apply to manually fitting CMEs as well. When you get the most dangerous Earth-directed CMEs, they're often accompanied by particle storms. And your coronagraph images then automatically degrade. Not automatically, they're inherently degraded by those particle storms. And you also get data gaps when they shut the instruments off for safety. Just at the time when you want to forecast the most dangerous CMEs. The most dangerous CMEs are often fast, so you'll have only 1 or 2 images before they disappear from your field of view. And they often don't occur in isolation. You get a sequence of CMEs from the same active region, and before one has left your field of view, another one has started. And that makes fitting very difficult for manual and automatic fitting. And another practical problem, of course, Stereo A has been sharing almost the same longitude as Soho for the last couple of years. That makes fitting very difficult. So on the top right here, we've got the solar wind velocity as estimated from tomography. And we've got the location of CMEs that have occurred over the last few days as those gray and colored circles. And we can feed that information into the highly efficient Hux-T solar wind model developed by Matt Owens and Luc Bernard at Reading. Hux-T is a highly simplified physics model, so it can run in a fraction of a second. So the forecast shown here shows 500 ensemble members. And what that gives us is a probability shown in the table in the bottom left. The probability that a CME will hit Earth or not, and also uncertainties in the arrival time and uncertainties in the arrival speed of those CMEs. Now, Vigil L5, the benefits, I think, are quite obvious. Since it's a space weather focused mission, it will hopefully give routine, regular, high cadence near real-time coronagraph data. That 60-degree, I think, is an optimal separation for automated CME detection and characterization. And from the tomography viewpoint, rather than needing 14 days of data, if we have a coronagraph at Earth and a coronagraph at L5, we can view the whole corona between them in around 8 or 9 days rather than 14 days, which is a real boost for the tomography. I'm not going to talk about heliospheric images, since there are other people in this room with more expertise, but I think that's one of the very, very important improvements offered by L5. I think from my experience with especially the automated CME detection routines, the future of space weather forecasting, CME forecasting, is machine learning. But also just to make the point that machine learning can be valuable for science as well. It's not just a black box. If you're training different models, it tells you something about the system, and it also builds up a catalog of parameters that would otherwise be inaccessible. You're making the most of the data. And those are my main points. Any questions beyond this meeting, there's my email, and there's there's 2 links. You can't see the bottom one, but if you go to solarphysics.abbott.ac.uk archives, you'll see all of them. There's a link to the detected CMEs in near real time over the last few months, and also a link to tomography over the same time period. Thank you.
Thank you very much. Great talk. Do we have questions? I think there's already one hand up there.
Really interesting. You talked about the future being machine learning. How does that fit into with the sort of BZ problem and CME BZ? Do you think machine learning can solve that problem as well?
Repeat the question.
The question is, can machine learning give insight into things like BZ and other parameters? My point for machine learning there is more for operational space weather forecasting. You've got multiple data streams that can tell you something about when a CME will hit Earth. You don't necessarily need a physics model to work that out, as we currently do. If you can train a machine learning system in the right way, but that's the critical question. Now you're asking about BZ, who knows? Yes, I think with enough data you can probably do it, but you'll need a system where you're not only feeding in coronagraph data, but also other types of data. And Siegfried is going to tell me otherwise.
No,
yeah. Yeah. Right.
Okay, this is a little bit blue sky research. In terms of BZ, I don't know if you know the RISE paper. So when the CME comes to the Earth and we use the data from L1 to forecast BZ with machine learning for the next few hours. It's not ideal because the CME has already hit Earth, but this is what we are testing in the Atmos work. If it can ever be implemented on a very short basis, because we have been doing for the last 2 years, on and off, we do it on and off. So although forecasting BZ from the sun to Earth of course, it's difficult. I mean, I don't think anyone can do it, actually. Maybe you, Ravi, can do it? Okay, this flux up, yeah, but this thing is quite interesting, yeah.
For CMEs or the
CMEs.
okay. Yeah.
Right. Thank you very much. I think we have to move on. Thanks a lot. Sorry for the tranquility, please. Here. Okay, so I think the next talk is an online talk, so we should get the fonts and everything as intended. I think.
I do apologize. I really
No. We will sort this out over the lunch break how we do this. And the next talk is by Duncan McKay, impact of an L5 magnetograph on non-potential solar global magnetic field modeling. And I think Duncan is here and
so we can say a screen.
Yeah, I'm here.
We can hear you and we can see you.
Excellent. So I'll just share my screen.
Yes, please.
That should, so I'll just share the whole desktop. And yeah, and start that.
Perfect.
Yep. So can you see everything there?
Yep, looks good. So whenever you're
okay then. So for the talk today, I'm going to discuss what impact a magnetograph could have observing from the L5 point in terms of improved accuracy for global non-potential modeling. Now, the work I'm going to present today essentially comes from two sources. Let me just jump back. There. Oops, sorry, it's going the wrong way. One was a paper. Can you see the bottom of my slide? Because I've got a bar. That's better. The source of the work today is a paper that I did back with collaborators back in 2016, but also at the end, I'll also show some results that a PhD student of mine has done who also considered what impact an L4 magnetograph would have as well on improved coronal modeling. So the main aim here for the talk is I want to determine what accuracy, what increase in accuracy we can have in our global three-dimensional nonlinear force-free field simulations if we also have extra magnetograph data from the L5 point. Now, one of the problems with carrying out this study is that we don't have long time series systematic magnetic field observations away from the Sun-Earth line. So in order to quantify what improvement could occur, I've decided to take a theoretical approach where I first of all construct a reference simulation, which is a simulation where we assume that we would have 360-degree magnetograph coverage. And that means we can include within our model the emergence of bipoles both on the front and back side of the sun as they would occur in real time. Next, from the magnetograms or the surface magnetic field produced from the reference sun model, I use them as observed magnetograms from the Sun-Earth line, and I then do limited data simulations where I only incorporate magnetic data either from plus and minus 60 degrees, which would be observing just from the L1 point, which of course is our current situation, or minus 120 degrees to plus 60 degrees around central meridian, which would arise if we had an L5 magnetograph. And from that, I can then quantify what improvement in accuracy I get by including L5 observations in terms of reproducing the reference sun model. So the first stage on this is, of course, to consider the model. Now, I'm not going to go into too much detail on this, as both Anthony and Jack will discuss the model, I think, later on. But the model that I'm using is designed to consider long-term simulations of the sun's global magnetic field over periods of months to years, where we study the buildup of free magnetic energy and helicity and electric currents in the corona. It has two components to it. It's got a photospheric flux transport model, which includes the emergence of bipoles. And also in the corona, we use a magnetofrictional relaxation. So as the surface field evolves, the coronal field evolves through a series of nonlinear force-free states. There, we're able to produce a mixture of highly sheared field lines, such as flux ropes, and also open field lines that are close to potential. Just as an indication of what the model can produce at the moment, just using L1 observations, what you see here is a comparison of an H-alpha image with a number of filaments and what the model predicted the sheared field lines or flux strip structures would look like after about 8 months of evolution. And as you can see, there's quite a good agreement there. So stage 1 of this project is to construct a reference sun simulation. This would represent what our model could produce if we have a full 360-degree magnetograph coverage. So in order to do this, I've produced a statistical emergence profile of bipoles that you can see in the top right over 2 solar cycles. So we've got the standard butterfly diagram. In total, over these 2 cycles, there is about 4,770 bipoles emerged representing active regions with a flux on the order of 3 × 10⁻21 Maxwells. Looking at the evolution of the surface field, but remember the model has both a combined surface and coronal field components, you can see that in terms of the emergence profiles in the activity cycle, there's no longitudinal dependence for the emergence of bipoles as occurs when we can only view the activity on the sun from the L1 point. So this would give us the ideal case of what we could produce if we had 360 degrees magnetograph coverage. The graphs in the middle graph shows just the variation of the surface flux, and the bottom graph shows the variation of the total magnetic energy throughout the cycle. So that gives us our reference model, and we now want to test how accurately we can reproduce that reference model when we only have limited field of view observations. So how do we actually construct these limited field of view observations? Well, on the right-hand side, we see 2 diagrams, one representing L1 and one representing L1 plus L5, where the zone shown in yellow represents the region plus or minus 60 degrees relative to central meridian for L1, where we can currently make accurate magnetic field measurements, therefore include bipoles within our code as they're seen to emerge. In the bottom image, you see the extended field of view that would occur with L5 magnetograph observations as well. Now, the important aspect from these pictures is the symbols. These denote where bipoles emerged in the reference sun simulation on this given day. And you can see there were 4 bipoles emerged, but in terms of the L1 viewpoint, our current situation, all of them emerged outside the region where we can accurately measure the magnetic field in order to include it within our model. So none of these bipoles could be included in the L1 simulation at the exact time that they emerged. Therefore, the L1 simulation would just have no field or very weak field at the location of these bipoles and would be inaccurate. However, what we can do is, as the sun rotates, these bipoles will eventually rotate into the field of view, and we can then incorporate them at a later time using the properties that they pass over the minus 60 degree from central meridian line with. So 3 of the bipoles in the L1 simulation, while none of these can be included at the correct time, they can be included at a later time as just an update once they come into the field of view. But doing that does mean the L1 simulation will be less accurate because you're having to include things at a later time and you're missing evolution and interactions that are occurring in the corona. You're missing the injection of energy and electric current. In contrast, if you've got the L1 plus L5, 2 of the bipoles now lie within your observed field of view, and these could be included in our limited simulation covering L1 plus L5 at the exact time with the same properties as they do in the reference sun simulation. One of them is then just included as a rotational update. So straight away, you see that the increased longitudinal range of coverage, that will make the model more accurate. The question is, how much more accurate will it be? Now, for both cases, there is one bipole which emerges far away from the field of view that would take on the order of 10 or 12 days to enter the field of view. That bipole is missed in all simulations as it's decayed. However, if there was an L4 magnetograph, that would have been able to capture it. So, what does the surface field look like? Well, here we just see an illustration on one day in the reference sun simulation where there is 6 bipoles emerging during a period of high activity. You can see that only 2 of them can be captured in our limited field of view L1, which is our present situation. But if we extend to have L1 plus L5, 4 of them are able to be captured within the model at exactly the same time as they were emerging in the reference sun simulation, therefore giving a much higher degree of accuracy. Just comparing the radial field going from L1 to L1 plus L5 to what the reference sun model, our target solution is, you can see overall, over all longitudes and latitudes, by having the L5 magnetograph and being able to emerge bipoles based on observations from it, makes the simulations much more accurate. So how can we quantify these results? Well, what we've done here is for the surface flux, the total magnetic energy, the electric current, and the number of flux ropes, I've considered over the whole time series of 22 years how accurately each of the limited data simulations reproduces the reference sun simulation in terms of the surface flux, the energy, the current, and so on, where I've plotted the ratio of these values within the simulations. The red curve shows the results for the L1 plus L5. Black shows the results for the L1 only, where for each case, the target value, of course, is 1. What's important here is the numbers that's existing above each of these graphs. These give the average accuracy in red for the L1 plus L5, in black for just the L1, but in blue, it gives the percentage increase in accuracy that we get moving from L1 to L1 plus L5 in reproducing the reference sun model. So in terms of low coronal modeling, in terms of non-potential low coronal modeling, that of course can simulate a lot of space weather producing phenomena such as flux ropes and so on, we're finding anywhere from a 26% to a 41% increase in accuracy for our simulations when we include the extra 60-degree longitudinal range of magnetograph observations that would be possible from the L5 point. Now, that first study that I carried out back in 2016 just considered what would happen from L5 point, but Anne Visserier, during her PhD thesis with me...
Sorry to interrupt. I think we are running out of time. Would you mind wrapping up, coming to the conclusion?
Yeah, certainly. This is my last slide anyway, so...
All right, great.
Yeah, so Anne carried out a study using both potential and non-potential modeling of what improvement can occur by having both L1, L4, and L5. So what you're seeing on these graphs, in these plots here, is the error in the heliospheric current sheet position at 2.5 solar radii, based on the target solution of the reference sun, depending on what magnetograph we have, depending at which point. Errors range from -70 to +70 degrees, where ideally we want colors to be green. That shows there is the least deviation in the latitudinal variation of the heliospheric current sheet. As you can see, L1 produces quite a bad result, very bad at cycle maximum, but not too bad at cycle minimum for the latitudinal displacement of the heliospheric current sheet. But going to L1 plus L5 and L1 plus L4 plus L5 gives a much better accuracy for the latitudinal displacement of the heliospheric current sheet as a function of longitude. L5 alone gives a 24% increase in accuracy over the 4 simulated cycles we considered. And if we included L4 as well, that would increase up to a 52% increase in accuracy. So magnetographs at both L4 and L5 can improve our accuracy by quite a high degree there. And of course, that's important for space weather models, such as the ones that Hugh was talking about before, because of course the heliospheric current sheet plays a role in these models. So that's my talk finished there. I've just put the summary up, so if there's any questions. Yeah.
Thank you very much. So I'm afraid we don't have time for questions right now, but I'm sure you'll be available by email, I hope, if people have questions for this.
Yes, if anybody has any questions, please just email me. And the thesis by Anne should be publicly available, I think, within the next few months. Yep.
Great. That's amazing. Amazing. Thank you, Duncan.
Yeah, thanks.
All right, and then we come to the final talk of this session, and it's by Tatiana Podlachikova about simulating high-speed solar wind streams from coronal holes using an L5, L1 observational configuration. Hi, Tatiana.
Hello, can you hear me?
Yes, we can hear you, and you can start and share your screen.
Great. Just to check, can you see a full screen or not?
Not quite yet, but I'm sure it's doing something. So. No, yeah.
And now?
Now we see your presenter view. If you swap the displays, then it should be okay.
Second.
Or you can just duplicate. That should also work.
Yeah. And now?
Yeah, now we see it. Yes, very good. Yeah.
Very great. Yeah, thank you very much for giving me an opportunity to present our studies. I will discuss how L5 can help us to predict solar wind at L1, and also why sometimes we see different solar wind velocities at L5 and L1, and also what is the role of coronal holes in these discrepancies. To simulate our L5 L1 configuration, we use 3 different scenarios. First, we predict from stereo B to stereo A, then from stereo B to Earth, and then finally from Earth to stereo A. Over the period from 2008 to 2010, when separation angle between these spacecraft was in a range from 22 to 90 degrees. We also detect coronal holes from UV images, and we consider a segment of coronal hole within 15 degrees meridional slice, spanning from minus 60 to plus 60 degrees. So this slice is roughly a 1 day of solar rotation. So the first thing that we do associations of coronal holes and solar wind. Here in blue we show coronal hole fractional area, and in red associated solar wind velocity. We just match peaks of coronal holes and solar wind. And in our example that we consider here, it's 2008, where stereo B represents L5 and stereo A represents L1. Separation angle between two spacecraft was in range from around 44 to almost 90 degrees, which give us from 3 to nearly 7 days for the solar wind at our modeled L5 to arrive at simulated L1. And then we adjust the time additionally just by accounting the distance of stereo A and stereo B to the sun, and this time is shown in red. And here we come to the first initial prediction for this case, where a blue line shows solar wind at stereo A, and a red line shows predictions just using data from stereo B. And these predictions for this case is already pretty accurate. It gives us root mean square of 75 kilometers per second, and for such little time, it's a pretty good prediction. But at the same time, we see that for some high-speed streams, for instance, 10, 9, or 13, we have strong overestimation. And for some cases, we have underestimation. We already know that there is a B0 angle, that is heliospheric latitude of central disk, central, or just in other words, just latitude of a spacecraft, can be responsible for changes for different velocities at different viewpoints. And here on the right y-axis, we show in magenta and cyan B0 angles for stereo B and stereo A. And if you look, we really see that the discrepancies in both B and A happen during large differences of B0 angle. But at the same time, for instance, for this case, we have overestimation, but neighbor high-speed stream already in pretty well forecast. Or for instance, here we have it looks fine, but a neighbor high-speed stream, we have overestimation. So it means that only B0 angle is not enough to decide whether we would have overestimation or underestimation. And now let's consider 2 illustrative examples. Here in red, we show high-speed stream from stereo B, and in blue, high-speed stream from stereo A. And basically, here high-speed stream that was observed on B is missed on A. And in dashed red line, we show fractional coronal hole area that basically sits close to high latitudes with a center at minus 51 degrees. And at the same time, B0 for stereo B that plays a role of L5 is also negative, minus almost 6 degrees. But at the same time, B0 angle for stereo A is positive, and the difference between these two B0s is pretty big. So it means that this configuration of kernel hole and B0 parameters can imply that we may expect that the wind that we observed at B would be decreased by the time it reaches A spacecraft. And here we have an opposite example where the wind that we see on stereo B will increase by the time it reaches stereo A. And here kernel hole is centered around minus 35 degrees, but B0 angle for B is positive, while B0 angle for stereo A is negative. And we can think of it like watering your garden with a garden hose. If a plant is sitting just in front of the central line of the hose, then it will get all the water. But if it's further away from the center line, it can get only splashes. And with this, we introduce a predictive indicator that is a function of latitude of coronal hole and difference between B0 angles. And we then plot this predictive indicator. I think you don't see my cursor. So the figure on the left with red line, we show this predictive indicator for this case that we considered in 2008. And blue line shows the differences between peaks in B1, L5 and L1, and large negative values indicator corresponds to very strong overestimation, while large positive value of this indicator corresponds to very strong underestimation. And we develop a set of critical thresholds that account for coronal hole latitude, coronal hole area, and difference between B0 angle, which we will use to decide whether we would have overestimation or underestimation. And on the figure on the right, we plot all values in red line of the predictive indicators that satisfy these thresholds, and blue line shows differences between solar wind peaks on L5 and L1. And we use this to build third-order linear regression that can help us to estimate the level of underestimation or overestimation in advance. And here, finally, we show adjusted predictions in green, and we see that all adjustments align well. For instance, number 13 is decreased, number 9 and 10 is decreased, number 28 is decreased a bit, number 30 is vice versa increased, while 31 is decreased. So we check this for all spacecraft combinations and years that we considered in this study. And we, on the figure on the left, in red bar, we show how strongly we have a drop in root mean square error of predicting peaks of solar wind velocity at L5 compared to initial forecast. And on the right, we show how, in general, these adjustments decrease the prediction accuracy of solar wind velocity at L1. So to wrap it up, I would emphasize three main conclusions. First, L5 and L1 configuration helped us to get valuable insights into relationship between coronal holes and solar wind. We show that this is a combined effect of smaller coronal holes located at higher latitudes plus B0 that impact differences in solar wind at both viewpoints. Larger coronal holes tend to deliver solar wind more uniformly. Second, we see that L5 offers a very strong potential for solar wind predictions at L1 with relatively high accuracy and large lead times. And finally, this study also shows how important is to have coronal hole information from instruments like UV imager on board of Future Visual mission. Yeah, thank you. That's it.
Thank you very much, Tatiana. Very encouraging closing words there. That's great. Do we have questions online? Any question online? Okay, then everything is very clear. Thank you very much, Tatiana, showing this. and also for introducing the space garden hose to us. I think that's the first. So thank you.
Thank you.
That brings us to the end of this session. Now we'll have a lunch break. I know that some people are trapped on a train. Some have now made it. So there may be a few changes in the order in this afternoon, but please bear with us. We'll do this. If you present in person in the afternoon, please come and see us now so that we fix those technology issues that seem to be going on here. But otherwise, I would say we'll meet again at 1:30 for a sharp start at 1:30, and I hope you have a good lunch break.
Okay.
Hey, welcome back, everyone. Time to get started again. For those of you who haven't seen it yet, our friends from Easter have brought some little giveaways over there. So some Vigil Mission merchandise. Please come and help yourself. All right. The first talk of our afternoon session is another invited talk. And it's a great pleasure to introduce Steph Yardley. She's going to talk about space weather science at L5, and that's about the combination of remote sensing observations and in situ measurements.
Great, thanks, Daniel. Yes, my name is Stephanie Yardley. I'd like to thank you for the invitation to be here today. It's nice to actually make it, finally made it in person. And today I'm going to talk about the power of combining remote sensing observations with in situ measurements and how this can improve or benefit space weather forecasting by having these measurements at L5. And so there's this, we talk about this space weather forecasting problem that spans about 8 orders of magnitude in space and time. And so this is from reconnection in solar flares all the way to the magnetic disturbances that you get in the magnetosphere. And so we have a flaring event that occurs on the sun. And then, of course, the arrival of the first photons is around 8 minutes, obviously because of the light travel time. And then if associated with an energetic particle event, so these electrons, protons and heavy ions that can get accelerated during these eruptive events, the first SEPs can arrive within as little as tens of minutes and then can remain high. The flux can remain high for several days. And then finally, we have the arrival of the CME itself, so these solar eruptions that come from the sun. Typically, they're about 2 to 4 days. We know in some more extreme cases, it can be on the order of a day. And so really, a lot of the forecasting we do, we can do some forecasting where we can try and give some percentages of when a solar flare can occur, for example, but a lot of it is done as in progress or now casting. And so ideally, we need to predict with advance warning, not just the occurrence of these eruptive events, but also things like the arrival time of CMEs, the Z component, is it going to be geoeffective at Earth, things like the strength and duration of the SEP events, and also the solar wind conditions. So obviously this is not a huge problem in the slightest that I've just described. But in general, to try and predict particularly the occurrence of these events, we need to understand a lot about the source region evolution, so the long-term evolution of active regions. And so why do we care? You've seen this many times probably by now. We care because of the space weather effects that result from these events. So, for example, the radio blackouts from solar flares, GICs because of CMEs, and then also things like radiation for astronauts and airline passengers and crew. And so, for example, if the National Grid wanted, say, a 5-day warning of a CME, we currently can't give that. And so this is why we're looking towards long-term prediction of the sources of space weather. And so now I want to talk a bit about the motivation behind L5 with Vigil. Obviously, some people have covered some of these points already this morning. But the key of having both remote sensing observations and in situ measurements at L5. So currently we have a lot of spacecraft that sit at L1. And so we're restricted, we've got a restricted view of the sun, generally between about plus and minus 90 degrees, although in certain aspects this is probably between plus and minus 60 because we have projection effects. And so by having a space weather monitor L5 like Vigil, then we can really extend our view of the sun surface by about 60 degrees. And so ideally with the remote sensing, oh, I've clicked off it now. And so ideally, by having remote sensing observations, such as those provided by a magnetograph, by an EUV imager like we've seen this morning, we can extend our view of the sun's surface, and we can have this long-term, we can have observations for long-term evolution of these CME source regions or even coronal holes. And we can also improve our magnetograms, so we can try and remove the 180-degree ambiguity by having these two lines of sight. And also, as we've seen as well, we can have these multi-viewpoint synoptic maps. We can also image this corona and solar wind along the Sun-Earth line. So this is good for seeing the CME evolution from Sun to Earth and giving accurate properties for solar wind and CME models. But also we can see whether an event is either front-sided or back-sided. And this is often a problem for forecasting. And then we have in situ measurements such as the solar wind parameters, magnetometers, and these can give us advanced warning of fast wind streams from coronal holes. Again, we've already seen some results that show this would be advantageous. And this can also help improve solar wind models, and then we can also have and track previous CME activity from source regions. So this idea, if say we have an active region that's rotating around on the sun, it's constantly erupting, we can see what orientation the flux rope has when it reaches L5. And so we can get an idea of what kind of structures we're going to see at L1 if it continues to erupt. And so these are the 3 points that I'm going to focus on because I don't have time to go through them all, and obviously other people will be covering these points as well. So a lot of what I'm going to show, I'm going to talk about are observations from Solar Orbiter. This is because it's a mission that is trying to explore the connection between the sun and the heliosphere. And the way that it does this is by having 10 instruments on board, 6 remote sensing and 4 in situ. And actually it's just reached its 5th, I can't believe I'm saying this, it's reached its 5th anniversary as it was launched in February 2020. And it's an encounter mission that gets close into the sun, so it uses Venus gravitational assists and gets to about 0.28 AU. And because of the uniqueness of the orbit, the telemetry constraints, and also the fact that we have partial disk images on board, then we have these remote sensing windows, which are roughly about 3 times 10 days in length every 6 months. So you can see an example of this orbit on the right, where you've got the orbit of Solar Orbiter, and you can see that there's these 3 remote sensing windows as it travels close in and around the sun. And so I'm going to start with the first point and talk about long-term active region evolution and observations from this. And so in order to get the observations during these windows, we have to plan in advance. So we call these Solar Orbiter observing plans. And so this one is just looking at the long-term active region evolution. And so it occurred in the first perihelion. So this was the remote sensing 3. So it was the end of March 2022. And the idea is we can monitor an active region for at least 10 days during this window. And also we can get, because of the position of Solar Orbiter, we can get these stereoscopic observations. So we can get a viewpoint, a 2-angle viewpoint of these regions. And so the observations took place at the end of March. And then we also had Earth-based assets as well, looking at the same region. And so this is the configuration. So while Solar Orbiter wasn't at L5, you can see that we get this multi-viewpoint view of this source region. And you can see the observations from AIA on the left, where you can see this active region that was being observed by Solar Orbiter and multiple spacecraft. And then again on the right by Solar Orbiter, you can see that there's less projection effects and we get a better view of the source region. And so this was the first eruptive flare that was caught by most of the, or all of the remote sensing instruments on board Solar Orbiter. apart from Metis. And again, it gave this stereoscopic and spectroscopic analysis of actually an erupting filament, as we'll see in a moment. And so the target for this soup, of course, because of where solar orbiter and Earth were located, then we could study the active region evolution from Earth with SDO for at least 7 days or so. And then the targets were chosen to be these 2 active regions here, and in particular this polarity inversion line where a filament formed. And luckily during the observations, there was actually 2 M-class flares. One of them was eruptive. And so what we actually saw was filament eruption along with this M-class solar flare with the CME, and also the you can see the energetic particles there as well. So it's a very well-rounded event that was caught during this time period. And so this allowed us to study the eruptive flare signatures from different viewpoints. So for example, here you can see in AIA, the view from Earth, we had you can see the filament, you can see the flare loops. And then again, the view is slightly better from solar orbiter due to the angle. And then we can see also the flare loops in 304 and 174 of EUI, the fulsome imager. So it was a great event to kind of test the ingredients of the 3D standard model. Does it hold up? And so it also allows us to determine the pre-eruptive structure of the region, and also what triggered the actual eruption. And so although we could see the filament quite clearly in AIA, it was harder to see what was going on in the HMI magnetograms because of the projection effects that we have. And so what actually happened in this case is we had this reverse S-shaped filament. And then we could see that looking at the theme magnetograms that you can see in the bottom, we could actually see this small scale parasitic dipole that emerges. And so we have this, if we imagine a flux throat configuration holding the filament, it actually rises and then erupts due to the emergence of the dipole. And now without having HRT from phi, it would be very difficult to see what was going on and to decipher what was going on due to projection effects. And so just to summarise this particular study, it's a great event to test these kind of models and study the 3D pre-eruptive structures of CMEs from multiple vantage points. The analysis for the in situ measurements is currently ongoing. So there was actually the CME hit, and also there was an SEP event at Solar Orbiter, Bepi Colombo, and Stereo A. And actually, if we think about tracing the evolution of BZ, just taking a look at the in situ data so far, then the configuration of the flux rope in situ seems to match what was on the Sun. Now I'm going to move on to the second point, and for this I'm going to talk about stealth CMEs. So these are CMEs which have weak or no low coronal signatures. These can be quite problematic for forecasting, particularly say if you have LASCO data and you can't decide whether it's a halo CME heading towards you or behind, or if there's data gaps. And so in this case, the forecasters thought that this CME wasn't actually directed towards Earth. And actually, it wasn't just one CME, it looked like a double-lobed CME too. And so after the event, when looking at the SDO data, we actually saw a very faint coronal dimming that occurred. That was the only low coronal signature that we saw, which indicated that maybe these CMEs were actually coming towards the Earth. And in fact, it did. So we actually had a G3 storm during this period. So we had a strong storm due to this event. And this therefore was difficult to forecast because forecasters weren't sure whether this was a front-sided or back-sided event. And so what we did to study this particular event from January 2015 was use these global coronal nonlinear force-free field models, which you've heard about earlier, and we'll hear probably some more this afternoon, to understand what was going on the far side of the Sun, and also what was actually erupting on the Sun, because obviously we don't have this view from L5. And so what we actually found is actually there was a large active region complex on the far side, and there was multiple flux ropes in the active region complex, and also on present where you see the dimming. And this looked like it was rising in the computational box and that it would be unstable. And so what we could do is we could take that initial global coronal field configuration and then feed it into a full MHD simulation. And we can actually see that there were these 3 eruptions that occurred here and 1 that occurred at central meridian where the coronal dimming actually occurred. And so what we learned from this particular situation is, I'll skip through, is that this coupled approach was very useful, and actually L5 would also be extremely useful in this case, because we had these 3 erupting flux ropes, and it was unclear that obviously the third one was actually a front-sided flux rope heading towards us, which actually had the same orientation of the flux rope that was detected in situ. Then finally, just to finish off, I want to talk about fast wind streams from coronal holes. So again, we're back to solar orbiter observations, and this was a fast wind soup that ran back in October 2023. And you can see in this case, solar orbiter is coming from the far side of the sun all the way back towards Earth. And so you can see that solar orbiter during this time period is about -32 degrees. And so the idea of this is to look at low latitude coronal holes and try and capture fast wind coming from these coronal holes. And this depends a lot upon these kind of magnetic connectivity models, and are we going to actually detect wind from this region in a few days' time. And so these are the observations we have. So we had the SDR observations here. We see a large, or actually 2 coronal holes attached to each other. And then we see that the connectivity points taken from the model actually fall within this hole. So we think that we're going to detect, we should detect fast wind from this hole. You can see the high resolution images like the line of sight magnetic field and also the EUV from EUI. And you can see this really nice fast coronal hole wind stream that was detected for about a 4-day period. So you can see the velocity, the density, temperature, and also the magnetic field as well. And what was actually quite nice about this particular period is not only was solar orbiter about -31 degrees, but also PSP was about -74 degrees. And so if you look to the right, you can actually see the various views from the different spacecraft. We have the view from Earth where we can see the coronal hole just rotating around, which you can see is at central meridian for solar orbiter. And then if you imagine you could see it from PSP, then you can see it's quite close to the west limb during this time. And so PSP actually detected the same solar wind speed. So whereas the wind arrived at solar orbiter on the 24th, then PSP actually detected this solar wind stream a few days earlier. So you can see this period where we've got this high velocity, and then we've got the proton density and temperatures again. And then if we look at the bottom, we've actually got this is the magnetic connectivity tracing back to the open field on the sun. So you can see this these 2 coronal holes here. And you can see that they're basically passing through the same wind stream, but at slightly different times and for slightly different time periods. And so then this solar wind stream was actually detected at ACE on the 28th of October. So again, a few days later. And so you can see how this would give us an advanced warning of a fast solar wind stream being detected at L1. And also because we'd have the remote sensing imagery as well to see the coronal hole. And so this did actually, a minor storm watch was issued, and indeed we did detect this high speed stream from the coronal hole. And so what I'll do is I'll wrap up there. I just want to say that hopefully from this you can see the advantages of having both remote sensing and in situ observations with Vigil at L5. So we can look at the long-term evolution of CME active regions or these persistent coronal holes. We can also understand the CME evolution from Sun to Earth, again with remote sensing observations. And then we can also, along with the in situ measurements, we can look at the properties of fast wind streams, improve the models of ambient solar wind, and also track these CMEs, the previous CMEs from these CME productive active regions. And so with this, along with proposed spacecraft at L4, I've even heard potential spacecraft going to the poles. Obviously, we've got Solar Orbiter that's going to the poles very shortly, and also potentially an L3 solar wind monitor. Then it'd be great to have this holistic view of the sun and hopefully improve our space weather forecasting capabilities. Thank you.
Okay, thank you very much. Excellent talk. Do we have questions for Steph? Everything very clear. Maybe I had a question though,
Yep.
and that was so these soup activities, they need some time to plan and to perform and then to analyze. While for Vigil, of course, we have much faster time scales. What do you think? How far can that be pushed, or to what degree do you think this could be automated?
Yeah, I think we need this kind of time to learn what we've learned from Solar Orbiter and Pulsar Solar Probe. Like you say, it's taken a lot of time, so I feel like there's still a lot of results coming out from these missions now, even though we've had them for like 5 or 7 years. And so I think once we've gone through these case studies, then we can use some of the tools that have been spoken about during this meeting, and even develop tools that can then help for more, operational purposes. So having this, because a lot of this was done after the fact, right?
Yeah.
And that's what we want to avoid. We want to be able to do it in real time.
But you have to prepare for it.
We have to prepare.
Yeah. Do we have online questions? Anything? Okay, then let's thank Steph again. Thank you. And we come to our next talk that's given by Matt West. And that's a status update of the ESA Vigil mission. Oh, I still get my tongue twisted. ESA Vigil mission. All right.
It's good on the screen.
Yeah.
Why isn't it on this screen? It's 20 years ago.
Yeah, that seems to work now. Okay.
Gonna give my presentation.
Yes, so.
Yeah. Okay, good afternoon, everyone. My name is Matt West. I think I know most people in the room, but if not, I recently joined the Vigil mission, and the talk I'm going to be giving today is on behalf of the Vigil team and all the instrument teams. And I must say, Steph just did a great job and stole most of my slides, to be honest. So that means we've got more time for questions. And in fact, if people have questions while I'm speaking, I'm happy to take them, just to, if it's going to be useful for people, if I answer those questions. So we've got the mission statement here. We're all aware that Vigil is being built as an operational mission to monitor space weather from the L5 points. And right from the offset, I want to say that we're building this mission to science grade standards, let's put it that way. So everyone can use this data, the scientific community can use this data, and it will not just be useful for the operational community. Alongside that, of course, and again, Steph covered this in her presentation, we're going to have early warnings, we're going to be able to forecast in advance, nowcasting. And one other thing which I feel a lot of people kind of miss off of their kind of list of space weather services, and that is long-term monitoring. And I think this is important for planning missions, or maybe if you are planning to go to Mars or whatever you're going to do with Elon Musk's going to do, you want to have an idea of what's going to happen in the future. So Vigil, through its consistent long-term data set, can help us with long-term forecasting, or monitoring, as I've called it. Of course, we've got the kind of the obvious advantages from L5 in terms of improved predictions of CME impact times and locations, and through the chronographic and heliospheric suite. The data is going to be operational 24/7, and because we're away from the Sun-Earth line, unless it's an extremely broad particle event or something like that, it means that we can actually get away from some of the the operational risks from being in the line of sight of an Earth-directed particle event, or CME. Low latency, I've said that a few times. And it's also worth just highlighting, this is ESA's first forecasting mission that's going to be positioned at L5. It's the first forecasting mission that's going to be at L5. So that should also be exciting. So how are we going to achieve these objectives and actually monitor the heliospheric environment in the sun? We've got 6 instruments in total, 5 which kind of we've called them core, as in they're being built by ESA, but we also have, which is no less important, the CFI, the JEDI instrument as well. So let me just quickly run through these. We've got the chronograph and the heliospheric imager. These are your white light images, white light or visible light instruments, which are going to be useful for monitoring space CMEs and flows all the way from the sun, from about 3 solar radii up to about 50 degrees. Then we have PMI, which is a photospheric magnetic field imager. For those who are familiar with SOFI on the Solar Orbiter platform, it's the kind of the next generation of that, which will be supplying our vector magnetic field maps. Then we've got 2 in situ instruments, the PLA and the MAG instruments, which will be helping us understand the solar wind environment, which will be similar to what we'll be experiencing at Earth in a few days later. And then we've got JEDI, which is the EUV imager, something which is close to my heart, and I'm glad that it's on there, which will be, of course, observing from the solar disk out to 3 or 6 solar radii, depending on which instrument in the JEDI suite you use. So I can whiz through this because Steph covered this in her talk. We've obviously got this Enlil simulation on the left here. And the reason I use this simulation is because it's used amongst the forecasting community. And Vigil is going to not only be able to supply new boundary conditions to such heliospheric models, but hopefully with our 24/7 low latency data, we'll be able to constantly update these models in semi-real time to help with our understanding of forecasting space weather at Earth. On the right-hand side, we've got our usual kind of EUV and white light composite image. Sorry, it's a bit dark up here, but these are obviously from the Earth perspective, which, as we all know, is located here and here. But because we're interested in activity traveling along the Sun-Earth line, we've got Vigil, which is going to be roughly located around here. These schematics are obviously not to scale or anything like that, bear that in mind, these are cartoons, but this is where Vigil is going to be located, and that's obviously going to help us with understanding what's traveling along the Sun-Earth line. But also, if we consider the rotation rate of the Sun, not only are we going to be able to see structures moving over the solar disk, so if we pretend that this is from the L5 perspective here, we will be seeing structures rotating around before they are Earth effective. But also, if we now focus on the Enlil simulation, you can see the solar wind streams in there. Although not exactly the same because we're looking at an outflow environment, we're going to get a good idea of what we can expect at Earth in the coming days through the in situ instrumentation, PLA and the MAG instruments. Again, these are not to scale, obviously, but we have obviously got the EUV instrument here, 0 to 6 solar radii through the 2 channels, through the 2 instruments. Around the outside, we're going to have the chronographic observations. And of course, my slides will run on. We're going to have the heliospheric images as well. And I've kind of caught this in one big box here. And the whole idea is that through these overlapping observations, we're not going to have the gaps. We're going to have observations going all the way through EUV visible light, all the way out to around 50 degrees, which is will be great for tracking structures. All the way almost to Earth. Of course, we've got to take into account the fact that we are going from EUV to visible light. We'll have to take that into account, but hopefully There's room for active research there in terms of how we can actually integrate these two different sets of observation. In terms of the mission, nominal mission life, we're looking at as of 7.5 years, but there will be consumables on board for at least a 5-year extension afterwards. In terms of how we're going to get there, we go into a geostationary transfer orbit, excuse me, before embarking on a 3-year transfer to the L5 point. But it's worth noting that operational phases are not going to begin when we get on orbit. We're going to begin when there's about 30 degrees separation with respect to the Earth and the Sun. And there is also the option that this transit time can be reduced to, say, 1 year if a direct injection becomes feasible. At the end of the mission, we have the end of life and disposal phase, where we'll passivate the spacecraft and free up the L5 environment for potential future missions. Where are we right now? So on this kind of crude Gantt chart I've put up here, you can roughly see most of the instrument development is around phase B2, pushing into phase C. And I think the important things to take away from this diagram are the instrument delivery window and integration, which we're looking at around 2029, and our launch, which we're currently looking at 2031. So that's kind of the timescales that we're looking at. Seems a long time in the future, but I personally want to be using this time to make sure that we are mission ready. And I'll be getting onto that in my summary slides, because I think it'll be useful for us to have a discussion about the way forward. So this is roughly what I've just talked about and through the mission statement. We've got our instruments here, our 6 instruments, integration and launch in 2031. I want to make the point again that the mission is being designed to deliver high quality observations. We are going to be calibrating the instruments properly and producing the necessary data sets for people to use this data for not only operations, but also for research. And although we're not going to be running any campaigns like the Solar Orbiter mission, we will be producing this consistent data set, which is quite powerful for anyone who wants to conduct long-term studies. And I think that's something that's sometimes missed with missions that have dedicated observation programs. And also in terms of the data that we're producing, we're going to develop it so it aligns with established standards. So this is the like the FITS and WCS standards, and also the CDF standards. And we're doing this on purpose because it will ensure compatibility with existing tools. We do not want to be reinventing a whole bunch of new tools. We want people to take the data and just throw it at things like SunPy or SolarSoft or AstroPy, and hopefully it will just work. And on top of that, with observational tools like HelioViewer and JHelioViewer. So I think that's going to be one of the powerful things about the mission, that we are going to have this long-term consistent data set. We're striving to make sure that the data is going to be freely available, and we're trying to adopt an open science distribution strategy. So there's not going to be firewalls or anything like that. So nobody should be afraid that we're going to be hiding it and doing crazy things with the data. We want everyone to have access to this data and use it. Because if people are not using this data, we end up with a mission that is exactly the same in 5 years' time as it is in year 1. We want people to use this data and come back with great ideas and new tools to kind of take the mission forward. In the spirit of this, it's important that we get community input, especially in this development phase. And this is important in terms of refining the data quality, but also identifying potential operational and research priorities that we should be prioritizing with the data in the future and as we develop the mission. And To ensure mission readiness, I would like to set up some semi-regular community-led meetings to kind of like foster this collaboration. And so I'm hoping people in this room are going to actively be getting involved, and we can get together and take the mission forwards. And I've kind of picked out 5 bullet points down here, and I'm hoping we're going to have a time for a very brief discussion afterwards. I want to understand the user needs, operational user needs as well. It would be useful to incorporate lessons learned from other missions, such as Solar Orbiter, making sure that we're doing this correct in the correct way. I want to work on enhancing existing tools. I do not want to be seeing people using, say, StereoCat, which is in the same way that it's been used for the last 15, 20 years. We've got these wonderful data sets coming up. Let's adapt these tools to ingest the new data and take them forward. And also, what new tools can we develop? And it would be great if the actual kind of funding bodies could create some channels for R2O grants, research to operations grants, so that we can take some of the research that's out there and turn it into active operational tools. And this is where I leave my presentation with. If there's any ideas, any questions, throw them at me.
Thanks. Thank you very much, Matt. So this is the opportunity now.
This one over here, Lucy.
You mentioned future and individual too.
Yes.
Plans back when we had used to give a talk, not that long ago, plans for
Sure. I mean, right now I'm focusing on Vigil 1. We should focus on Vigil 1. Maybe Giuseppe, you want to
yeah. I mean, indeed, because it's an operational mission, indeed, we want the continuity of service. The plan is, I think, this year, end of this year, we should do CDF studies. When we do 3.0 study for Vigil 2. So we'll scope out the instruments. There's other aspects that we will also include in that study, so a bit of on-board processing. But that's a sort of time frame. Linked to that as well, we've also put forward some activities in our technology development department, directorate, for possible sort of instruments as well. So we need to start with the instruments as early as possible, so that we kill the risk. And by the time we actually kick off Vigil 2, that's we're in very, very good shape. This is a direct lesson learned from Lagrange. We want the instruments well progressed, so that when we really kick off Vigil 2, we're in good shape to embark on.
So we have to repeat a couple of things for those online, including the questions. Sorry, I forgot. I forgot.
No. Do we want to repeat the question?
No, we don't have to repeat the question, but just the point about Vigil 2, maybe. Yeah, that there's later this year going to be pre-phase 0 for Vigil 2, end of this year. So online people too, be ready. Hey, it's another question over there.
This is a question about spacecraft operations.
Mm-hmm.
So I'm curious about the Vigil mission supposed to navigating the dust moons in the L5 region.
That's a good question. So,
some long question.
Sure.
Because the nature of the moons can be significant movements for the senders. Because one of the reasons TUP has failed is because of IMU failure. So what kind of mitigating strategies are you employing with this?
Okay, so let me paraphrase your question. You're asking about the dust environment that we're going to experience around L5 and how this might actually interfere with the detectors and the sensors. And potentially you're saying that Stereo B was, that the failure was created by this? Okay.
Spacecraft believe that it's spinning and you try to adjust its attitude, where it spent equation fuel and trying to adjust attitude.
Sure.
So I spent battery.
Mm-hmm.
So NASA couldn't turn back to the spacecraft.
Yes.
And try to reposition it.
Sure. Okay, so you're kind of delving into areas that I don't know so much about, but I know there has been some studies looking at the degradation of the stereo missions as they kind of pass through the instruments, I should say, not the mission, the instruments, as they pass through those points. the L5 and the L4 positions. And in terms of the detectors, I'm not aware of massive degradation when they went through those points. That's the first thing. Maybe I'm missing something in the study that I'm not aware of. But I know that ESA have conducted some, not reviews, what's the word I'm looking for? I'm going to say studies again, of the region in terms of the dust environment they can experience there. And in terms of us building the instrument, we are building it in a way to ensure that we are hopefully going to be fully operational. Giuseppe, maybe you want to take this one?
The FDR, failure detection, isolation and recovery, is really pushing the maximum availability. What you're describing there sounds like a specific cascade of events which led to the loss of mission. And we've seen this on other missions. But our FDR is really designed to be for as fast as possible, and also it makes use of techniques which are already well proven in other missions, other deep space missions. So let's say not first time we've had a safe mode in the science mission, and we would make use of the safe mode of Vigil, which is exactly the same as the safe mode of the other science missions, or use of practice. So I think it's quite robust and more proven. These sorts of things indeed are ones we fear, where you get a cascade of events and you end up in a situation where the power of the point in the safe mode we have on the kidney based on the safe mode. I think that's the one.
That's the one. His answer. Peter, please.
Peter, yeah, one quick final question.
Why does it take long?
There's another question for Tiff.
I don't understand why this takes to 2031.
That's a good question. That's again probably another one for you.
I'm thinking large express would be a picture showing they can do things very quickly to do the mind. Is it a budget? Is it a launch date?
Well, actually we use the spares from yeah, so you use the spares from the you have to build the units ready to go. That's not the case for Vigil. We have to build the units from
there shouldn't be any design.
No, they're not designed. Only some of the units are designed. Jedi is not designed. Prehistoric imagery is not designed. PMI is not designed. So the only ones which are full heritage is MAG and PRA. So say that we're using existing software. PMI, for example, is really a new generation. The other issue, just to say, is indeed a funding issue. We did not get all the money from the Ministerial Institute, which meant we had to stretch the project. And then 25, that really, and this is where we need the science community also help, is to lobby the member states to make sure we get all the money we need in NCN 25. Otherwise, I will face another delay. I will have another year for this if I don't get all the money that I need. So it's really critical that everybody in this room supports the lobby that I do, does. In the industry, we have a project manager that's working very hard to lobby. But we're not science missions, so we have to fight for money every Tuesday. I have to go back again in 28 to get money to the conflict and the money to the operation. So it's really good. I have a huge fight for money.
All right. I think that's encouraging all of us to do meetings like the ones today and the ones that you have listed there on the board. So thank you very much, Matt. All right, and that brings us to the next talk by Anthony Yates. Yes, it's you. Anthony will talk about constraining coronal magnetic helicity. And I think we got the slides. Oh, yeah, that's a bit jumpy, but there we go. All right.
That's the arrow keys.
Yeah, that was.
Okay, thank you very much. So I'm sort of going to carry on, I think, from what Duncan Mackay was talking about this morning, but unfortunately I didn't make it here in time to hear it. So apologies if I repeat what he already said, or someone else already said this morning. I really just want to make sort of one point here, if you like, which I don't think will have been said by anyone else, but we'll see. And that is that observations from L5, and from Vigil in particular, and in particular magnetograms, will really help us to constrain the magnetic helicity of active regions, so in global models of the corona or in local. So what is magnetic helicity? It's a conserved quantity in any highly conducting plasma, so like the sun's atmosphere. And it just comes about because basically magnetic flux tubes or field lines can't pass through each other. So for example, if you have a pair of kind of linked magnetic flux tubes like this, then they can't unlink. And so that kind of locks in a certain amount of magnetic energy that you can't release by sort of relaxation. Now, in the sun's atmosphere, we don't usually have closed tubes like this. It usually, the field lines usually either start or end, or both, on the sun's surface, and they're kind of line tied, as we call it. But that line tying means that you still have a kind of topological barrier to undoing twist and complexity in the field, at least for field lines where both ends are on the surface. And if you can see the point. So if you have a field line where only one end is on the surface and the other, it disappears out into the heliosphere, then there's basically nothing to stop these ones from untwisting. And so you don't tend to store helicity in those regions of the current. So mathematically, helicity is sort of associated with a scalar density of A dot B, where A is a vector potential for the magnetic field B. Don't worry too much about the equation. I just wanted to make the point that it just follows from a combination of Faraday's law and Ohm's law that this density obeys a conservation law here. It changes by a divergence. So what that means is if you integrate it over a volume, then you get something that's conserved and only changes by flux through the boundary of that volume. So in the case of the sun, the boundary is the surface, if you like, and this flux would correspond to things like the foot points moving around and twisting up the field lines or untwisting them. But it could also be the emergence of a new active region, like we saw in Steph's talk, where it's already twisted when it comes up from inside the sun. And so those two things will both be a sort of flux through the lower boundary. These are two simulations similar to what I hope Duncan showed you this morning. And they're running for something like 10 years or so. And obviously I've opened out the whole sun so you can see it in one picture. And I'm showing you magnetic field lines colored by their contribution to the magnetic helicity. And the top one, the new active regions emerge untwisted. And I think that's probably what it was like in simulations that Duncan was talking about that we did back in 2016 about the L5. But what you see is there's still helicity in the movie. And this is coming, if I can play it again here. This is coming because the foot points of the magnetic field lines are being sheared by motions on the sun's surface, even after the regions have emerged. And the dominant one is the differential rotation, which because it's a large scale. And so you're still generating helicity. The bottom one is the same, but the only difference is that the active regions, when they emerge, are given a twist. And it's actually quite subtle, the difference. So if I pause it at a suitable time, you can do a sort of spot the difference here. So for example, this active region on the left here, you see in the bottom one, it's got sort of darker blue field lines and they're more twisted. There's more of a sort of reverse F shape. And that's because of the helicity that emerged in that region that wasn't there in the other case. And similarly, it's sort of stronger in some of these other regions. But overall, it's quite subtle when you just look at it like this. So, but if you integrated numerically over everything, you can see the difference between the runs. So that's what I did here. So each of these symbols is a different simulation run. And I just averaged over the whole 10 years the amount of helicity, essentially. And that's on the x-axis. Don't worry about the details here. The y-axis is the free magnetic energy in the simulation, similarly averaged. So the energy above a potential field. So this is energy that would in principle be available to power eruptions and so on, and probably does power some in the model. So you can see there's just basically a good parallel kind of relation between the helicity and the energy. In case there are people here who are more interested in the technicalities, that you've got to plot the right thing for the helicity. If you just use the quantity that solar physicists call relative helicity, which some people have probably heard of, you'll just get nonsense, because it's a signed integral. So the positive and negative regions are just going to cancel out. And they're not actually connected in reality. They're on different sides of the sun and so on. And so you have to be a bit more clever and do what I call here the unsigned helicity. And the idea of this is that you basically split your volume into lots of individual flux tubes. You can think of one around every single field line, in some sense. And then you can integrate your A dot B within those tubes, and each of those will be a conserved quantity, assuming you fix the boundary. And so then you can take the absolute value of those and add them together, and you get a sort of unsigned version of the helicity. And you can see it correlates with the energy. This is the same x-axis, the same simulations, but the y-axis is now a measure of what I called eruptivity, so the sort of eruption rate in the simulation. And it's actually a measure of sort of a burst of magnetic flux coming through the top boundary in some highly averaged way over the whole simulation. And what you can see now is that these simulations split into sort of two branches. And the difference between the branches is basically how I twist the active regions when they emerge. So the black dot in the bottom corner is the one where they emerge untwisted, the top movie, and the others are where they're twisted. And so I've listed all the active regions in the simulation, latitude and time. So over 10 years, you have the sort of whole solar cycle, essentially. So in the bottom branch, the red ones, all the regions have the same amount of twist in some measure. The same parameter that twisting them up, except that I put them opposite signs in each hemisphere, which is what you observe. Whereas the top branch, point at this bit, the top branch, it has the same, oops, go back. It has roughly the same, the same average amount of helicity, but the individual regions have values that fluctuate around the mean. So I put in some variability, and the consequence of that is, as you can see, that you get more eruptions. And it's basically because you have more local kind of concentrations of helicity, and it's when you have a concentration of helicity usually that you get an eruption, loosely speaking. And so for the same average helicity, you get more of them if you concentrate it in more. And so the consequence of that for things like space weather is that we really want to have a good idea how much helicity each individual active region has. And so this brings me to back to the point of L5. And the problem is that so these simulations I showed you are very parameterized. We don't really have a good observation of the amount of helicity in each region. We have to really do it from statistically, almost. But the thing with helicity is that it is a conserved quantity. So in principle, we can get an idea for the amount of helicity in the real region if we follow what's going on the boundary in that active region. And that's much more reliable than trying to extrapolate the non-potential magnetic field in the region, which is essentially impossible on a global scale. And so this is, of course, the sort of well-known thing in solar physics. You try and measure the helicity flux in active regions. I'm going to show you here just a quick movie. This is a simulation done by Steph here, I believe, which the idea of this is that they followed a single active region, and they did this for other regions as well, with a sequence of magnetograms. And so you can calculate that flux term for the helicity in principle. But what they do is drive a simulation with that And so they build up, and they showed that you can build up quite accurate sort of distributions of twisted field within the region compared to things like EUV loops. But the problem with this is that you only see active regions at the moment when they come around the side of the sun. And so you can only measure this flux input after you see it. And so the point is really simple. If we have observations at L5, we will have a longer time series of the helicity flux. And so we'll almost certainly have a more accurate idea of how much helicity the individual regions have, among other things. So that's really the point I wanted to make. So thank you very much for this.
Thank you very much. Do we have questions? And I think we have a microphone. Any question? Everything clear with questions online? All right. So then, thank you very much, Anthony.
Thank you.
Great. Let's thank him again. And the next talk is by Jack Reed. I think we have the slides already here. I have quite a long title, but that's great. Thanks very much. So look.
Okay.
It's about strong magnetic skew in the solar corona. There we go. That's it. All right. I'll also give you a sign.
Thank you. Perhaps I could have put in a shorter title by suggesting that what I'm going to speak on today is simply our ability to model the production of one contributing factor in space weather, namely fluctuates, and how that ability is affected by our current limited field of view, and of course, speculatively or optimistically, how that might be improved by an L5 mission. We're interested in fluctuates which are strongly twisted magnetic fields, which are important to us for several reasons, including the fact that they can support the dense accumulations of matter in the corona, which optically we can observe as filament, with one good example here at Central Meridian. More generally, fluctuates have a number of interesting properties. First is the presence of strong magnetic skew, which I'll define shortly, which is useful in studying fluctuates in any given magnetic field. Secondly, is the very long lifetime of fluctuates, which last on timescales significantly longer than the solar rotation timescale, which is one of the reasons that our limited field of view becomes significant when we try to study them. And thirdly, the reason we try to study them is that those lifetimes have a propensity to end quite rapidly and violently in eruptions like this, whose geomagnetic effects are somewhat obvious and which are one of the contributing factors driving space weather. Given this, it's important and useful to be able to model fluctuates from their genesis throughout their lifetimes until a possible eruption. So we'd like to see if we can predict when fluctuates will begin, how long they will last, and eventually the moment at which they might erupt. In order to do so, it's useful to have to consider this quantity of skew, which I mentioned earlier. If we consider polarity inversion lines in the sun's magnetic field, then high above the polarity inversion line, the coronal magnetic field can make an angle to the normal to the polarity inversion line, which we call gamma. The skew in this way was introduced by Sarah Martin and her co-authors in the 1990s. However, its study goes back slightly further in a different form, studied in a different way by Roy about 10 years earlier, who observed that filaments have what we would now recognize as very strong skew by looking at the angle of between filaments and between the barbs on filaments and their axes. And Roy concluded what we would express now as the fact that filaments or fluctuates have very strong magnetic skew, typically around 70 degrees. And thus we can diagnose the presence of fluctuates, such as may support filaments, through the presence of strong magnetic skew. In order to calculate that angle of skew and therefore to identify fluctuates, in principle this can be done through a magnetic field calculated in any way, such as derived directly from observations, but here we do it through numerical simulations through nonlinear force-free models of the kind which Duncan, Anthony, and Steph have mentioned. The internal physics are relatively simple. We just solve parallel equations. The boundary conditions are more interesting and are where we shall see the limited field of view to be significant. For the magnetic field, it's important to be able to include the emergence of new magnetic flux on the sun, constrained by magnetograph observations. And for the velocity, we can use the well-constrained processes of surface flux transport. Both of these cause the sun's magnetic field to depart from equilibrium, introduce non-potentiality, and will give rise to fluctuations. In general, however, the tendency of the coronal magnetic field is to try to restore equilibrium, which we represent by including this magnetofrictional form for the velocity. This causes the sun's magnetic field to tend back towards a force-free state. Full details of the model are available in Duncan and I's papers from 2006. And using this method, we'll simulate the sun's corona at a period around solar maximum, particularly from September 2014 to March 2015. For flux emergence, I mentioned the importance of including new flux, which we can detect through magnetographs. Doing so is very important in maintaining the accuracy of these models and their ability to reproduce coronal phenomena. However, in this, we encounter the effects of our current limited field of view. We detect flux through magnetographs, of which all existing ones, with a narrow and relatively recent exception of solar orbiter, are on the Sun-Earth line. Hence, while we can reliably detect flux such as emerging at these locations marked in green, we can't necessarily detect it elsewhere, much of the photosphere, which is shown in white, is missed. Given this, it's quite natural to ask how likely we are to see the production of strong magnetic skew, which characterizes fluctuations within our current field of view. And when we're thinking about a possible extension to that field of view, would this be improved if we had a different vantage point? Right. In order to begin to answer that question, we start to look at the presence of magnetic skew in our simulation. In black and white contours, I've shown the magnetic field on the sun's surface, similar to the plots which Anthony showed. In the colored line, I've shown the angular skew along various polarity inversion lines, where the warm reddish colors indicate dextral skew and the strong bluish colors indicate sinusoidal skew, although the chirality is relatively unimportant for the study. So where we see the strong red regions such as this, we notice the presence of fluctuations, and similarly, we can note the same about strong blue colors such as this. Invoking Leroy's observation that fluctuations tend to have an angular skew above 70 degrees or below minus 70, it's the absolute value which is seen here, we can identify specifically those areas where we have the strong skew defined in this way. And we see those in the yellow and blue objects that we've identified here. All of these are fluctuations, and any of them potentially could be supportive of filaments, and any of them could be liable to erupt. Given this, we wonder how long it takes these to form. In order to do so, we perform a correlation analysis between the emergence of a new magnetic flux in the sun, which is limited by the range of longitudes in which we can observe flux, and the creation of strong magnetic skew, such as present in fluctuations. An aspect of the way in which we insert magnetic bipolar regions, which is related to one of the points on which Anthony touched, is that there is some magnetic skew associated with an emerging bipolar region, which is why we have a spike at 0 days here. Aside from this, however, it tends to take 15, 16, 17, 18 days after the emergence of flux for strong magnetic skew to form, and thus for filaments to grow, for fluctuations to grow. Which is interesting if we compare with the solar rotation timescale of 27 days, and gives rise to a natural limitation on our models, which is a consequence of our current field of view. We can only insert flux in our simulations on the Earth-facing side of the sun, but by the time fluctuates form, they're typically on the far side. Moving on slightly more speculatively, slightly more optimistically, we wonder if this could be improved by a different vantage point. We can currently detect flux and incorporate it in our simulations either if it emerges on the Earth-facing side of the Sun, or if it emerges on the far side and after it's rotated onto the current field of view. So would this be improved if we could detect flux earlier and therefore include it at what we often call its dynamic time when it truly emerges in our models? Answering this question is, of course, very difficult because we don't actually have magnetograph data for the far side of the Sun. But we can mimic that effect. And we do so by inserting simulations in our models 2, 4, 6, 8, and 10 days earlier than we currently do, with properties appropriately adjusted to reflect the evolution that would take place in that period. If we observe bipolar regions earlier, they would typically have higher flux. Then we simply ask, how many of the features of strong magnetic skew, how many of the flux strips lie within the field of view, and of those, how many formed within the field of view? And here are the results showing the proportion of all flux strips in the field of view which formed there, in green by number, in magenta by area. But the general trend is the same. As we insert them early, we typically see a growth up to about 6 or 8 days. And therefore, if we are able to insert particularly detect flux about 6 or 8 days earlier and include it in our models, we're much more likely to be able to see the formation of flux strips on the Earth-facing side of the Sun. So, given that strong magnetic skew forms in timescales comparable with the solar rotation timescale, we face the natural limitation in our models that when we model the production of flux strips, we can typically only model that on the far side of the Sun. But this would be improved if we could insert flux a bit earlier, instead of only within the narrow proportion of which we can see from Earth or from L1. In particular, there's a significant growth after about 5 days. Now, detecting flux on the Sun 5 days earlier is, given the solar rotation rate, equivalent to being able to see about 60 degrees further round on the Sun than we currently can. And 60 degrees behind Earth in its orbit is, of course, why we're all here. So it is likely that Vigil would improve our ability to model the flux strips on the Earth-facing side of the Sun. However, we do see these proportions are still scarcely about a half, and particularly the proportions which we can model start to decline at about 10 days. And the reason for this is that in this study, we're only able to model, again, a narrow range of longitudes in which we can observe flux, simply shifted slightly further behind from the current field of view from Earth. It remains the case that we're missing much of the Sun. And so this touches on a point which Steph made at the end, namely that L5 nodes featured to model the formation of flux strips on the Earth-facing side of the Sun completely. What we really need is total coverage of the Sun, but particularly with magnetographs, which has been proposed in a variety of missions, such as the 4Pi or Firefly mission, from which I borrowed this diagram. And on that optimistic note about convincing space agencies of the need for more satellites, I'll finish. Thank you.
Right, thank you very much. Do we have questions for Jack? Yes, Jonathan.
Let's try to read it. Is it constant, the timescale for rotation and timescale flux formation? So,
I suspect so. It's very difficult to predict the timescales for the formation of flux strips. It's simply an innately complicated system that's driven by a huge number of processes, and if you plug in all of those processes, the number you get out is about half a solar rotation timescale.
All right, cool. Well, thank you very much for your talk. Let's thank you again. And our next talk is by Craig DeForest. It's an online talk, very early in the morning for Craig. And he will talk about the synergies between Vigil and the Punch mission, which will actually launch very soon. Synergies for space weather science. I hope, Craig, you can hear us.
I can hear you just fine. Can you hear me?
We can hear you and we can see your screen. Perfect.
Wonderful. Good. Okay, so let's see. I will be brief. This is about synergies between L5 and the Punch mission. I'm so delighted to be able to talk with you folks. I haven't been in an RIS meeting in some years, but I just wish that I could be there in person. Launching in, what is Punch? We are a constellation mission of 4 cameras that work together as a single virtual instrument. We'll be imaging the outer corona from about the LASCO C3 field of view out to about 45 degrees away from the sun. So an enormous field of view, trying to capture the structure of both the solar wind itself and the large space weather relevant features within it in 3 dimensions using polarization. So we're launching into sun synchronous polar orbit in about 2 weeks. And as you can imagine, preparations are at a bit of a fever pitch. These are the cameras we're using, or instruments, though I like these days to think about Punch as a single virtual instrument. We have a coronagraph built by the Naval Research Laboratory here in the US. On the left, we have 3 copies of a wide field imager, which echoes the stereo high that was developed at RAL so long ago. They're both powered by detectors built by RAL Space, which has just been a real privilege. This is an image of the 4 spacecraft right now, or I guess 3 days ago, in the clean room out at Vandenberg Space Force Base, where they're being integrated to a deployer assembly and rocket. So these are pretty small. They're about 1 meter long and something like 70 kilos each. This is how they work together. On the left, you can see a simulated forward model of Punch data. So this is a simulation that was done at APL, Johns Hopkins in the US, broken apart, and we made simulated observations and then stitched them back together using the Punch pipeline. And Matt West, whom we recently lost, much to our detriment, and whom you just heard speak, was involved in some of the development of that pipeline. Anyhow, the field of view looks a little wonky. Out to about 80 solar radii, it's continuous all the way around. Beyond 80 solar radii and out to 45 degrees, we have these gaps which rotate with the orbit. Each of these jumps represents about 8 minutes of time. Very far from the sun, we operated about a half-an-hour cadence. What you're seeing here is 4-minute updates and 8-minute rotations. This is just some of the science that's not CMEs that we're looking at. We're interested in these stream interaction regions. This is one of the very few movies of a stream interaction ever made. It was made with stereo high 2 some time ago. You can see the overall sort of snail shell appearance of the CIR as it comes rotating around. We'll of course see that in 3D. Why are we using polarization? We're using polarized light to measure the 3-dimensional structure of CMEs. Here's a typical halo CME seen with LASCO C3, again, some time ago. I think this is from 2015. It's just a very well presented one. By tracking the leading edges in 3 dimensions, you can see the ambiguity we're trying to overcome for space weather forecasting is this ambiguity that we're all familiar with between a wide, slow CME and a narrow, fast CME. So by tracking the apparent leading edge in 3 dimensions, we can discern arrival time. And of course, by using one field of view, we overcome the major problem with forecasting not just the arrival time of halos, but the degree of a glancing blow that CMEs might deal to the Earth if they're coming off center, which is that forecasting the arrival and strength of the CME requires, among other things, finding the shape and location of that front. If you're using parallax from multiple viewpoints, each instrument sees a different leading edge because of the different angle. And so that couples the modeled shape of the CME to the modeled location of the CME in a way that makes it hard to forecast, not just when it will arrive, but whether it will arrive strongly. So we tried to overcome that with polarization by extracting three-dimensional location from a single viewpoint. There are other ways to do that, of course, and we'll hear Bernie talk about one of those shortly. We hope also to measure the chirality of CMEs as they leave the sun. Once an event has left the surface of the sun, there's no current way to actually measure the chirality in the short term. Again, several folks, including Bernie, have developed ways to make informed guesses as to the chirality. But by tracking the three-dimensional structure of internal substructures in CMEs, we hope to measure that directly en route. This is what we're doing with polarization, measuring the location of things, the degree of polarization of light, reflects the scattering angle, that's the upper left here, that leads to being able to solve for this triangle on the lower left, which tells us where the feature is. The downside of polarization as a sampling tool is that it's double valued. So these curves here show the degree of polarization versus the three-dimensional out of sky plane angle. And you can see that there are two angles that yield any one level of polarization. So we have to apply tracking of the features to disambiguate that. And I'll demonstrate that in a moment. So for the remainder of this talk, I'm going to talk about some of the reasons why this is hard, talk about the background subtraction problems we have to solve, the geometry that we have to deal with. We couldn't actually get rid of all the geometry. And then I'll show you a hare and hounds result. Polarization, well, subtracting white light, I think we're familiar with the difficulty of that. The signal that we're looking at far from the sun is as small as 0.1% of the total brightness entering a camera. So that's a challenging background subtraction problem. To do that same, make that same effort with polarization requires an order of magnitude more effort, because we have three separate polarized backgrounds, each of which imposes its own errors on the three-dimensional signal. We have to subtract all three of these in different reference frames. Fortunately, we managed it. We had to develop a new formalism for, or rehash an old one maybe, for representing linear polarization. That's this MZP system on the left. These are three different views of polarization space. I wanted to show you the diagrams, but I don't really have time to go into the details of the theory. But Matt, who's there in the room with you, can probably help talk about it during the break, because he helped develop the paper that we wrote on this. So we use this MZP stands for -0+. It's a three polarizer system. It uses three ideal polarizers, and it allows us to subtract backgrounds because each of the values is positive definite. So we've identified a helpful analogy between polarization space and color space. And so MZP is analogous via that mathematical analogy to RGB space, which helps build some intuition. I'm sorry I don't have more time to talk about it. Moving on to geometry, trying to forecast the arrival of a CME means you want to find the leading edge of the CME, the direction of propagation. What we see in the two-dimensional plane is a locus that's offset from the nose of the CME. And so capturing that is important. It's a smaller problem than the overall parallax problem, just because the relative offset and angle is less. But this is a picture of an ice cream cone model showing the leading edge on the image plane from an observer at the left, and that's this dark line near the top where the line of sight is tangent to the CME. And what you really want to find is this point where the dashed line coming from the sun radially outward intersects the leading edge. And so there's a small correction to make for that. We did a hare and hounds exercise to see how well we could locate CMEs in 3 dimensions. Here's some simulated data from another modeling run, similar to that movie that you saw earlier. Over on the right, this is after just a simple background subtraction using only the spatial information. Of course, you can use spatiotemporal information as well and do a better job, but that's what we did for this hare and hounds exercise. Nathaniel Laurent is an intern that we set at this problem last summer. He did a fabulous job of it. He'll be presenting at the Punch 6 meeting for those of you who can attend either in person or remotely there in a couple of weeks. So these are the results that Nathaniel got from the polarization inversion on the forward modeled data. The goldenrod disk here represents the sun. The observer is at the origin over on the left. These blue dashed lines are the ghost trajectories that we rejected because they had a non-radial trajectory. Over on the right, the orange curvy lines are the forward modeled inverted location of the CME. And the purple line here is the leading edge location as modeled in the simulation. The black line here is the forward modeled center of mass along a given line of sight. You can see those trajectories are slightly different. I could go into the geometry, but I think we don't have time. But Nathaniel will be talking about that at Punch 6.
Great. I'm actually, yeah, you're right. We are slowly running out of time. If you wouldn't mind. Oh, I see. Okay.
This is my conclusion. What I wanted to highlight actually here was this is an S-curve, and so it's not perfect, but it's good. It lines up well. So we're seeking to track large features with polarization. The strengths are complementary. Vigil will be seeing the leading edge along the line between the sun and the Earth, but won't have the ability to directly measure the lateral position. Of course, Earth-located images can do that. Cross-validation is going to be very important, and we're looking forward to joint studies to do better than either of us can alone. So go Punch. That's all.
Very good. Thank you very much, Craig, and thank you for taking the time in this very, very busy phase of Punch at the moment. I have time for one quick question, if there is one right now. No, it seems to be all clear. So I think also go Punch from our side here in London. Thank you very much. And then we come to the next talk. And I see Volker already appeared on the screen. And this is by Volker Bothmer about enhancing space weather forecasting, analyzing CME events for ESA's Vigil mission. And we can already see your screen. Great.
Yeah, good afternoon, everybody. And you can hear me?
Yes, we can hear you. Yeah, very well.
Good. So I will talk about what we learned, something of what we figured out being of key importance for improving forecasts with Vigil. So I have next to me Enno Müller, who did a tremendous job in the modeling and in the simulations. So this is a slide we can almost skip. To the left is the halo from L1, and we get into a better perspective with the L5 mission with respect to sunrise events. So for the ESA L5 utilization study, we made use of the stereo A and B satellites, which went through L5, as we already heard, plus SOHO LASCO from L1. And so the details are not so important, but we noticed a couple of things which I will refer to in the next slides. So this is a sample event we have looked at in that study. It's a halo. You can see the halo to the northeast and southwest. And that would be interpreted most easily as one single halo. But if we take the observations from the vantage points of B and A, to To the left, you see we denote CME1, CME2. And indeed, what we see in A is the same thing. We have two CMEs which happen at about simultaneously. And so that's clear that we will make a huge step ahead if we have multiple viewing points to avoid these misinterpretations. So here's a fit by treating the halo seen by Lasko as a single event, and this is the refinement achieved by knowing that there are two CMEs happening at the same time, and one is directed towards Earth. This is a general problem that we figured out in many events. We have complexity because of CMEs happen very close to each other in time, almost sometimes simultaneously. But also we have the problem that often a series of CMEs merges into a compound stream of multiple ICMEs in the interplanetary medium. And that has led to a lot of misinterpretations or pitfalls in previous studies, even those that have been published. So how to come across a little bit further with these problems? So we try to look at events where we have three viewpoints and CMEs which appear distinct from other events and ICMEs which were not compound streams. So as a baseline, to the bottom you see, to the right bottom, ICMEs of the Richardson-Kane list, and K. Gopalswamy used that list to study 45 events with the advantage of having three viewpoints. And we had a look at these lists, and we took those which matched our criteria that we have no overlapping CMEs and no compound streams. And then what we do, we apply for the CME the well-known GCS model in Python, and we derive the apex speed. And the next thing is, in a coordinate system in 3D, we can infer where the apex of the CME is situated with respect to the position of the Earth. You see that in the upper right grid in blue. The red dot is the Earth. And the speed is typically in a self-similar expansion model of a CME slower at the flanks of the CME than at the apex. So from knowing where the apex into which direction it goes and where the Earth is situated, one can derive the ratio of the speed in the direction of Earth, which is important to get arrival time values, and that's I'm coming to. Using this apex speed, we further use it as an input into the drag-based model. And here we calculate our own gamma parameter, which is based, as you see in the bottom. We take it constant. We have also a model where we vary it with a variable gamma value based on some other assumption using Helios data, but that's a different story. So then we derived the cross-section of the GCS or of the CME from the GCF fit and use an empirical mass relation, which we derived from analyzing a great number of CMEs in 3 dimensions. You see this formula for the mass to the lower right. So doing this and applying it to the events we selected out of the previous studies, you see here some results. The observations time in core, the event number, the Earth-directed speed from GCS, the 1AU time of arrival, and this is for the ICME and not for the shock, so we always distinguish between the shock arrival time and the ICME arrival time. And then in the last column, you see the difference to the actual arrival time, the time we calculated, so we're getting to a few hours away from the actual arrival time. And to the right, you see the differences in the arrival time or the error. And these are just a few events, but so that would mean we would need to validate the concept with many more events. So we come to arrival time errors of about 4 hours for the CME compared to the typical values of 10 hours. And what I like to point out is what we learned from the WSPR observations, from the new observations from PSP WSPR, that you see here the WSPR inner field of view, the WSPR outer field of view, and you see the enormous complexity of the flows seen in the inner and outer fields of view of WSPR. Maybe you noticed that there were, I let it run once more, a very big CME to the top, and then a couple of streamers, and a lot of small plumes-like flows. And then you see here to the bottom a number of CMEs which merge or interact together. So I think turbulence is widely underestimated in its role. And we don't know how far out we have to treat turbulence, but I like to add to Quay's talk that I believe that the Punch mission will substantially be able to add knowledge to this subject. So my conclusions are, of course, we need multi-point observations, and our method in reducing the complexity, treating the events led to pretty good arrival times in the simulations, and the new observations, as I already said, by PSP WSPR, show the importance of to include turbulence if we are studying or doing forecast with VGL. And I can also say, go Punch. Thanks.
Thank you very much, Volker, for this very clear presentation. Do we have questions for Volker's presentation? I would have one about the turbulence point that you made. What is the main impact that you see from the turbulence? Is it through the compressive structures and the flocculants that you have there, or what is the connection?
Naja, if you run the drag model, usually we assume that we have a homogeneous flow of solar wind between suburbs. And if that is not the case, it will substantially change the derived arrival times in the propagation model.
Oh, the propagation, okay.
And so in the events we looked where we get pretty good arrival times up to the hour sometimes. We have events where we have looked at the medium Sun-Earth is unperturbed before the event, pretty much as good as we can judge this. But also with WSPR, the turbulence is not, of course, not necessarily the same. It will develop on small scales, but here I was emphasizing on the large scale role or the turbulence of large scale structures. And we should try to understand how far away from the sun the turbulence gets eventually smoother. But it should play a role in the propagation models.
All right, thank you. Thank you very much. Do we have other questions or questions online? It's not the case. Then thank you again, Volker. And then last but not least, we come to the talk by Bernie Jackson, considerations of the use of an L5 mission's remotely sensed heliospheric imager data in conjunction with similar instrumentation near Earth. And so we can see you, not the screen yet, but I'm sure that's coming up in a moment. Yeah, very good.
Hello, can you hear me?
Yes, we can hear you. And we see the slides.
Yes.
Very good. All right.
Well, these are the folks that helped me on the work. I'm going to talk a little bit about the various structures. I want to show you what an L5 mission can do in conjunction with instrumentation near Earth. One of the systems that we use near Earth is interplanetary scintillation, and I have this old website that runs and has been updated a lot throughout the the time periods. And here you can see what we can show from that. If you look at predictions DV, you can see what's happening in an ecliptic cut, a meridional cut that goes through Earth, and a whole plethora of different locations around the inner heliosphere using this this technique we have. You can also animate this with a little click here, and you can watch how things progress over time, including in fact at Earth, where you can see the structures tracked that are seen in the volumetric data that we produce. We can do the same thing with Thomson scattering brightness near Earth, and I show you this experiment. This is the solar mass ejection imager that was developed back in the the last century, I guess. Anyway, it took a bunch of strip images from a sun synchronous orbit at 840 kilometers. And from that, you could deal with these data in a tomographic sense. Now, what you can do with this, and very similar to the interplanetary scintillation data that I show, is to take a line of sight, which is in this case, an expanding cone, as you see in the lower left. You take the weightings that are present in brightness from this data. We only had brightness there. And from that, you could look at each line segment and trace them back to a source surface. The source surface is shown here for the Thomson scattered light. These all emanate from sort of the sub-Earth point. And at one time you see this, at another time you see a slightly different version, and the weights on these are all different. And from that you can make a change to the model. You can formally invert the changes that are needed on the surface, and from that produce a new three-dimensional model, and that least squares fits the observations. You could continue to do this in an iterative sense until you get a converged set of density. We've done this now and gotten this so that we can get resolutions of about 1 hour in cadences and 1 degree by 1 degree for structural shapes at 1 AU. And you can see here at the upper right a time series and what is produced over a period of, in the upper left part of this, this is a whole Carrington rotation of data. Below that are small bits of 1, 2, 3, 4, 5 days, and you can see how this very large structure that occurred on May, it was a complex of CMEs, could be viewed in situ, either by the ACE or WIN spacecraft. And both spacecraft gave slightly different answers, at least for the peak of the structure that you see there. But much of the variation in the structure is captured by both spacecraft. You can take the volumetric data and look at it carefully and then see what it looks like. And it's kind of a mess. And as you can see over on the right, in different perspective views. If you make an cut through the ecliptic here, you see the structure isn't very regular. This was noticed. This isn't quite as good as we can do now, but you can see a lot of structure in this complex CME that arrived. And over on the right is a face-on view of what passed the Earth at this time. So that's actually in high resolution. These things seem to be mottled and corrugated and not a nice smooth front. For instance, this little feature here, if it really is continuous, if it takes about it's about this goes past at about 600 kilometers a second. So depending on whether you're here or here within a few degrees, you would see something that was plus or minus about 6 hours of a front. Okay, we can do the same with stereo. And this is a time when stereo A and B had just been launched. And you can see the two spacecraft over here on the left, they're really close to Earth. They were able to see in the ecliptic plane, of course, here as a sky map of what was seen. Here you can see an ecliptic cut, and you can see the two spacecraft here. The stereo, well, in this case, behind looks in front of the sun over on the west side, and ahead looks to the east. And this gives you, in fact, a view of all the fine scale structures here. You can take this and look at what's seen in situ up at the top. And this is a whole Carrington rotation, but here's this portion where this structure came through. It was the most dense structure in this period in solar minimum. And there's just an awful lot of structure here. And you can see that same thing in stereo. This is stereo A. You can see the same structure in stereo B, but it's different. It's just not the same because it's in slightly different location. I took the same for this May 10th, 2024 event that was such a large thing, to take a look at what stereo A alone can do. And here you see what stereo and HIs reproduce at where they were. They weren't close. Here's Earth and here's stereo A in this ecliptic cut. And so you could see a number of things that were present. And of course, we also put this together with the interplanetary scintillation velocities to get a flow that we could measure. Over on the far right are the two. This is what wind saw, and here is what the stereo saw. And they saw different things, and we were able to reproduce them pretty well with just the stereo HI reconstructions. Here you see another example. We do this in real time now, or near real time. It takes so long to get from from APL to NRL to RAL, and then we have a mirror site that we can use these data from stereo A, and so you can show what is occurring 6 days following the current time, where you can more or less completely reconstruct the volumetric data. I was able to do the same with this experiment. This is the Parker Whisper data, reconstructed in 3 dimensions and shown relative to the IPS data that's used from Earth. So you see here a CME that moves outward with a 1 hour cadence. I show it. Earth is here again. This is 1 AU, and you can see a lot of structure in 3 dimensions that's present as as Parker moves outward. This was the actual view from the Whisper data, camera 1. I'd be remiss if I didn't say we've used this same technique to work with punch. And here's punch. What you can do here, we don't have punch data yet. So you can take the densities that are present in from the structures that we reproduce, and this is that May 30th, 2003 event that I showed you earlier. This is the plot of the sky map at this one time. Here is the density that's present below it, that's made directly by this technique. you can take either brightness and from the lines of sight that you get, make a pseudo map of densities that come from the densities that you reconstructed. Here is a polarization brightness that gives you the densities that are that were present, and here is again brightness obtained from a ratio of polarization brightness and brightness to give you the densities that you originally had here. This is the October 30th, October 28th big storm that occurred, and here's the direct view, and here's the ratio view that was done, reconstructed. Now there's a slightly different level of background that's used here, but essentially you get back the same structure. And again, it's not a simple structure. This is probably the shock that's extended out to this direction, and it's spotty, it's corrugated, and it just isn't continuous like you would hope to have a nice CME front. The conclusions here are, well, interplanetary scintillation can be used in a time-dependent 3D reconstruction in conjunction with heliospheric Thomson scattering images to provide outward flow. Solar mass ejection imager, SME, stereo HIs, and Parker, which are now provide rather good 3D analysis near your spacecraft, can be used with each other to give even a more robust perspective view. You can actually put all these data together and get perspective views from the different instruments. It'd be a good idea, in my opinion, to consider these near systems for use in conjunction with L5 imagers as inexpensive supplements. Thank you.
Thank you very much.
Still there?
Bernie, are there questions? Does anybody have a question about the presentation? Is anything online?
There's a lot of stuff there.
All right. Well, thank you very much, Bernie. All right,
Okay.
so according to the program, we have a few minutes time for discussion. And I think because Matt started this nicely with his questions, I'm sure, Matt, you'll be around a little bit, maybe a few more minutes or so. So if people want to raise those points more in private with you, they can do this. But otherwise, I mean, has anybody thought about it? Do you have any other points that you would like to discuss at this point, maybe triggered by Matt's invitation? Yes, please. Hold on, I'll bring you the microphone.
I just have a question to ask. So the question is that is the quantity already sort of fixed? Because that would probably the cadence most important for the sense instruments. If not, maybe I could see where as a scientist could maybe suggest particular goals or cadences or things that depending on what kind of science, because there's not a variety of science that I can think of. And obviously cadence can be something. But then from what I understood, once it fits, we should have two or three operational goals.
Okay, so good question. And this is exactly the kind of conversations I want to be having over the coming years, because we do want to take this into account. Now, we do not want to be having dedicated science programs or anything like that. But if there are good reasons to be using instruments in certain ways with certain cadences and certain resolutions, we want to be kind of organizing that now rather than after we launch and playing around. So we need that conversation over the next few years to make sure we get this right. And I've said this a few times, I do not want visual to be, it's an operational mission, first and foremost. We're producing the data in a way we're going to produce the data in a way that's going to be good for the scientific community. But what would be great is if this is not a static mission. What I want is, I don't want to be doing the same stuff in, 15 years time as what we've been doing 10 years ago, because I do feel like the operational field is a tiny bit stagnant. And I think a part of this is a disconnect between perhaps what the scientists can bring to the operational community. And so I think there needs to be some kind of discourse between us. And so it would be great if we can organize some kind of sessions where we can actually talk about this. And if you've got ideas, then let's try and not only bring them to the table, but also maybe you have ideas for operational tools which the operational teams are not aware of. Because often when you go and survey the space weather operational community, you will say to the operators or people who are running the programs, what do you want from such a mission? And the only tools that they're familiar with are the ones that they've been using for the last few years. It's not their fault. And it's also not necessarily the scientists' fault, because we don't have funds to turn our science tools into operational tools. And so the two communities have to kind of get together and see how we can take this forward. So that was a very long-winded way of answering your question, saying, yes, we need to be talking about this right now.
Jackie, anything online? There's that.
You seem to be taking on
No, it's
on Solar, we started, I can't remember how many years ago, the amount of analysis related to this. But I think that worked really well. So that was bringing in people who were not directly in the solar community, but had expertise to help. Is there something like that envisaged that you can pull in the expertise of people with modeling, etc., that are not directly involved in digital or the operations, but could become operational tools?
Yeah. So of course, all of these things require turning a science tool into an operational tool requires some funding, and I'm not sure what kind of avenues are available through either ESA or in member states. That's something else to talk about. But one thing that I would like to set up are a little similar to the solar orbiter working groups. I think they were very powerful and very useful, and it would be useful if we had similar ones perhaps for visual going forward. So that would be good. And if people want to kind of take the lead in some of these working groups, then let's get together and talk about it and take this forward.
That's very good. Other comments? Yeah. I was on the opposite side of the room.
Sorry about that. So I wanted to ask a question about thinking beyond visual too.
Yep.
I think there are very good reasons why we've chosen to start L5, but I'd like to get people's views and speak about these colleagues in if when we buy follow-on missions. Should we start L5 or should we launch certificate? Go back stereo idea. You know, we talked about the need to cover the whole, all 360 degrees of the sun, or just to manufacture self-similar machines in the store, let's say 5 seconds. So, just a general question there.
I think a lot of the answers are going to revolve around money. That's what it's going to go down to. But you know, you could even consider something more exotic where this is not going to happen, where you put something at L5 and when it's reached the end of its life at L5, you push it off into a stereotype orbit. But I think there's somebody wants to say something.
Yeah, on the start, I was going to say. I'm not clear. I was just thinking, we saw some of the science presentations today that were actually suggesting the more of a holistic view you get, the better, right? So there was definitely a case already made.
I guess what Sammy followed on the time with that, starting to see some commercial space for the ventures, nothing large. ESA, have any thoughts about that? Trying to push the commercialization of this sector forward? There's a lot of questions about
I don't know if I'm the best person to answer this or to speak on behalf of the whole of ESA. Do you have anything to say in particular, Giuseppe?
There's no plan to do a visual recognition in the private. Part of the big doesn't do private. But the space weather sort of what this space with the name of the plan in ESA is capable of taking many data sources that we already have payloads on the meteorological satellite. And I know that CF20% of them is still from private a couple of Earth orbiting missions or based on CubeSat or based on SmallSat. That could become sort of public-private partnership type thing or take the data of the service. So now whether that's commercially viable, because it's one thing to have the ideas, another thing to actually be able to sustain the commercial business. Is another, but yes, it's being thought about. But I don't think I think the mission-wise individuals or that scale today. I mean, Visual 2 is not being discussed as being a commercial mission. It's really thought of as being a follow-on institutional mission. Good. See this one again.
I'm excited with you. I think we will see commercialisation of this. What was the Grammy project? Or into what Henry's visual project? We did discuss whether it could be done in the next time. I think the challenge you have, and we see exactly the same challenge in terrestrial ecology, is business model. Because space weather and terrestrial ecology is about sharing data globally. That means you have one person taking the data and sharing it with the centre. So that is a big issue we need to get to. But I think maybe not Visual 2. I think pretty soon after, I think will be in the same space with the service. I'm certainly getting inquiries from people who want to ask whether I've got money to supply data for them. So it's not far away, I think.
Cool. I think we're coming close to the end of our time. I want to just have a few last announcements, but maybe is there any burning question, anything else left in the discussion that you want to ask now? Okay. Well, then, thank you all very much for this discussion. I'll have one quick announcement following on is a big word, but this was a really great meeting already, and I want to make a quick advertisement for another great meeting. And that's this one again. So, and that's just for everyone, because I think you all will be interested in the things that are discussed at that meeting. There's also a space weather part, of course, associated with it, but also the science side. And it's a very special thing that this meeting that only takes place every 3 years will actually be in the UK next year. So please save the date. SolarWinds 17 will happen in Bath in June 2026, next year. With that, I'm basically getting close to the end of the meeting. I want to say thank you, especially to the RAS that is hosting us here, that have really put everything together so that we can be here in this amazing place and have our really inspiring discussions. And especially also to Richard and his team sorting out all the logistics of this. Also, very big thank you to Jackie and Jonathan, who have organized all of that together with me in our team here for today. The speakers, especially the invited speakers, the representatives of the project from Airbus and from ESA who are here today. There's still some merchandise on Steph's desk there. So before you leave, make sure you pick up some badges, keychains, pins, and so on of the mission. And last but not least, a very big thank you to all of you for coming, for participating so actively, showing your science, discussing your science. And I hope the discussion continue and that this is not the end, because we're just at the start with Vigil. Thank you very much and have a good weekend, everyone.